and I will. Yeah.
Now I can hear you.
Hello.
Yeah, but I can't see you. You have not.
You
turned
can
on-
see me?
Okay.
Yeah.
Yeah. Okay.
Mm.
Turn it off. Camera and mic.
Hi, Shocking. Shocking, your audio is not connected.
Hi. Hi, Rohit.
Hello, sir.
Hi.
So we
Hi.
are live on YouTube,
Okay.
but we will
Okay.
start
Okay.
in some time, sir.
Very good. Very good. Professor Michael, can you hear me?
I can hear you. Can you hear me?
Yes. Yes. How are you?
Okay. Good morning or good afternoon.
Yeah. Good
Okay.
morning.
I see.
Still
So
winter, right?
I mean, for the audience, you haven't opened for them to join. You say the 500 audience. For those
These are-
which is the workshop, I see the participant on 8. Is that participant 8 is because 8 people are speakers here or?
Yeah, so we have around 550 registrations. So, but
Yeah.
selected participants have the Zoom link, and others will can see the workshop on YouTube. And
Okay.
there we have enabled the chat. So if there are questions on YouTube, our team can take it up and pass to the moderator.
Okay.
Rohit, can you share the YouTube link also with me? I can,
Yes,
you
sir.
know,
Yes, sir. I will
moderate
post
it.
here.
Okay. So Professor Gettu will be joining soon.
Yeah, I see somebody in the waiting room. You need to admit somebody.
Hi, Dr. How? How are you?
muted.
I think you
Oh,
are on
he's
mute.
muted.
Yeah.
Yeah. Thank you. I'm good. How are you?
Very good. Very good.
Nice.
So I think it's near to 9:30 a.m., right?
Yeah. It's morning here, but it's a storm today.
Oh, storm. Okay.
Yeah.
But I can see a nice view behind you.
Ah, that's the Northwestern. It's in Chicago.
I think Rohit, this is not your time is not BST. His time is GMT, not it is should be GMT. And we are not in BST anymore.
Okay.
But it's right, it's 9:30 a.m. but it should be GMT, Greenwich Mean Time.
Yes. Yes.
Yeah.
So we will be starting in next 7 minutes.
Mm.
Uh,
So I mean today I also have an interview for lectureship, so I might join drop in. Okay, so 12:30 if there's a close mark, if I'm not here, please just close it because I did depend on the interview process. Okay, sorry.
yeah. Your talk is in the starting few minutes only.
Yeah,
So
to talk, I'm fine. I can give a talk that's
Yeah.
after in the beginning, and interview
Yeah,
start 10. Yeah, 10 quarter past 10. I think we panel start 10. Yeah.
I think you'll
Good
be able
morning,
to
Mike.
make in both the places.
Yeah.
Good morning.
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 Have you back to campus, work in campus, or you're working from home? Most of
We
you?
are working from campus. Our campus initially during the first wave, it was closed. Then after that, it was opened, especially for the research scholars. And now
Mm.
slowly our BTech students started coming back.
Mm.
Yeah, but it was always open for research scholars. It was closed for the starting few months, and after that it was opened.
Mm. Our campus is open, but today is closed because of the storm, bad weather. It is real serious. Not as bad as it was forecast yesterday, but the campus is closed today because the red warning. Not our area, somewhere in the southeast area, southwest areas, but we are in the amber warning areas.
Oh,
So you have a storm with a wind speed of 60 to 80 miles per hour. It's
Wow.
quite strong wind. Yeah. But our campus back students, 50% on campus, 50% off campus. We offer this 1 week on campus, 1 week online mode. The government obviously push everybody back to campus, and they want everything to be normal. but still, last week we have 2 colleagues who tested COVID positive in the department.
Oh,
Of this,
okay.
yeah.
The cases here were always coming. In fact, with the faculty members also, most of the faculty members were, infected with COVID, and then now it's new normal. So what to do?
New normal.
Yeah. So now we are not that much afraid. So if somebody is getting positive, also we'll be saying, okay, why don't you go to your home, take rest, come back in 7 to 8 days.
Yeah.
Especially with this variant.
Yeah. You don't have to. I mean, hospitalization is much lower. So most people
Yes.
just getting. I think my 2 colleagues, one of them is was symptoms was very serious. So he felt the cough a lot and congested and feet. So he had lay down in bed for 1-2 days, high fever. But otherwise, just nothing. He says nothing. Is everything normal? It just tests the positive PCR, but it doesn't fake thing.
I think Professor get to join. Professor Ravindra get to. Yeah, Rohit, can you take care of the waiting room? Because,
Hi, Michael. Can you hear
Hi,
me?
good morning, Professor Gato. Good morning.
Hi, how are you? Hi, Penkun.
Hi.
Yeah,
Professor.
we're fine, thank you. Today we actually UK has the London areas a serious weather, bad weather warning, so university closed for today, just for 1 day.
Okay.
So, and there's an amber warning in the southeast of England and red warning in the southwest England. So we have a
Okay.
experience.
And that is because of bad weather.
Yeah, bad weather storm. Wind
Storm,
speed
okay.
60 to 80 miles per hour.
Okay, so London will be hit.
Yes, that's why
Okay.
all work from home today or closed for today.
Okay.
Things are okay. How are you? Okay.
Very good.
Very
Good to be here.
Nice to meet you. Yeah.
Yeah, we could not meet in person, but it's good to
How
be
about
here online.
the conference in the Gordon conference is this
Yes.
week, right? Is it
Well,
open?
the
Is it-
Gordon conference has been shifted to July. It will
Until
be in
July,
July.
okay.
Yeah.
Okay.
So if you're
Hopefully I can join in
interested,
July.
if you're interested, you can still certainly come.
Okay, it's same place in Italy
Same
somewhere.
place. Same
okay.
place.
Okay, I will check. That's good news.
Sure.
Okay, welcome to you come to visit Brunel once if you.
I will certainly want to.
We'll try to
I
plan
would do
one. Let me make an arrangement, and when it's
Okay.
closer time,
I'll tell you.
Thank you.
Thank you, Michael.
Yeah, Professor Good, today I'm interviewing lectureship for our department, and I will.
Okay.
It's a joint between. We have a program with Beijing University of Technology, so joint school. So we recruit teaching staff for 2 departments, civil mechanical and engineering. So I have been involved in the interview. I wasn't involved, but one staff has been panel member was failed ill by COVID, so I have to. Get in the position. So I will join in later on. Just
Okay. So Rohit, are you managing the program or is it Surinder?
I'll be doing it. Rohit will be taking care of the background and everything else. So we'll be starting in next 30 seconds.
Yeah, we are already live on YouTube.
Okay, that's good.
Yeah, we'll start in next 30 seconds.
Okay.
Rohit, how many participants are there on YouTube?
$33 are live on YouTube, and
okay,
we have 21 on the Zoom.
Okay. Maybe somebody has to take care of the waiting room because I could see. I'll
Yes,
also
sir.
do it. Okay.
Yes, sir. Sai Shri and Haripan are there in BTCM office,
Okay.
so we are coordinating from here, sir.
Okay. I think we can start now. Okay. A very good morning, good afternoon, and good evening to all the participants, speakers, colleagues, students, and my friends. My name is Surendra Singh, and I am an assistant professor in the Department of Civil Engineering at the Indian Institute of Technology, Madras, Chennai, India. And I, on behalf of my organizing committee, welcome you to the India-UK joint workshop on concrete waste recycling. So let me just briefly outline the genesis of this workshop. So this workshop is being conducted on successful completion of the UKRE DHT sponsor research project entitled A New Framework of High Value Added Zero Waste Recycling of Concrete from C&D Waste, jointly conducted by IIT Madras, India and Brunel University, London, UK, in collaboration with our Institute of Eminence Research Initiative on Technologies for Low Carbon and Lean Construction. Professor Ravindra Gettu will be talking in detail about this project, and Professor Michael will also be giving an outline on the project very, very soon. So this workshop is of 3 hours, and we have planned to cover the most hot topics related to C&D waste, that is material processing, policies, C&D waste management, and life cycle assessment. In the end, we have kept a dedicated session on special topics on C&D waste recycling, wherein we'll be discussing the current and future scopes of C&D waste recycling. We ensure that all the participants will be getting benefited from this workshop. The academicians, especially the young researchers, may get some new ideas for doing their research on. The field engineers who are attending may get to know the techniques, the state of the art to handle the C&D waste. So please attend the entire workshop. And now, without wasting any more time, I request Professor Ravindra Gettu, who is the chair professor and dean industrial consultancy and sponsor research at IITM, to officially welcome this program and highlight some of the aspects of our joint collaboration. Professor Ravindra Gettu.
Thank you, Surender. It's certainly good to be here. As Surender said, at the end of this project that we had with Brunel University, it fits in very well with our group that is working on technologies for low carbon and lean construction. My slide should be visible. Is it, Surender? Slide is visible?
Yes, I can see.
Yeah.
Yes, I can see.
So Professor Manu Santanam, my colleague, heads the group which is working on this technologies for low carbon and lean construction in the Department of Civil Engineering principally, where we are bringing together construction materials, construction management, and building science and automation experts. We are about 20 faculty members, about 30 research scholars, several collaborators from around the globe, such as some of the people who are attending here, including Michael from Brunel. And we have potential for collaboration with many organizations such as ACI and RILEM. So the critical questions that we are addressing in this program is shown here schematically. We have a lot of waste generated in construction and in other industries. We would like to know if we can use the material waste in a positive way, not hurting the environment, but helping the environment by using waste coming from agro industry, from other manufacturing sectors, and construction and demolition waste. We also have a lot of process waste. Process waste is the wastage of time, manpower, resources, and so on. So we have what are called the 7 wastes of lean construction. The wastage in terms of inventory or having the inventory sit idle, waiting till tasks get done, time, defects and their rectification, overproduction, where we have, for example, more concrete that is needed in the truck and it has to be thrown away. Motion, that is labor, movement of material, transportation. Can we save on transportation of material by, say, fabrication nearby, and over processing? Are we putting too much of processing, energy and so on in construction to give us? If we take care of all this, we believe we are moving towards sustainable construction. So our approach is a systems thinking approach, where we start off with the problems related to waste management, construction process management, help in reduce the deterioration of concrete structures, delay demolition if needed, and look at the life cycle carbon footprint. And you will have talks on many of these aspects during this workshop. For this, we need basic scientific research combining physics, chemistry, computing, and sensing. So we have a lot of resources allocated to that. We want to develop technology that can be transferred. We are thinking of test beds for both materials and automation, leading to more efficient management of the whole construction cycle, the management cycle, and this will also require policy. So we are looking also at policy being changed, and we have a group which is looking at policy also. So all these are the critical questions that we would like to address during the life of our initiative on technologies for low carbon lean construction. So here we are looking at the entire lifespan. We are seeing how we can use as much waste as possible as raw materials for construction, optimize the material supply chain, looking at waste that is easily available, locally available waste. We are looking at mapping of waste. We want to design more efficiently so that there is leaner construction, less wastage of time and resources and material. Look at construction that can be more automated. For example, we have a case of the first 3D printed home or house in India on our campus through a startup called Twasta, who is collaborating with us. Once construction is done, we are emphasizing durable performance as long as possible, such that we can estimate a long and use a longer service life. Once the service life is completed, we have to go for efficient demolition, collection of the waste. So we are looking at how we can map waste, see how much waste is produced and where it can be used in recycling. So this is where an initiative on the test bed comes up, where we are looking at material that can be judged easily, checked easily if it can be used as a raw material in construction. Some relevant topics relevant to this workshop that we are looking at. We are looking at high volume usage of waste. We are looking at both the physical and chemical processing combinations to make waste appropriate for construction. Use of process waste in robotic precast construction, pavements, and so on, as the first set of introducing such waste into construction. For this, we have to correlate the material characteristics to the concrete that is finally being used, ensure translation from the lab to the field. Then we have to optimize the usage of the recycled material, make sure the right type, the right amount is used. And we want to have maps, first countrywide maps that will look at the availability of materials that can be used in construction. So this is one of the tracks where we are looking at an integrated test bed that we are very excited about. The idea is that this test bed could quickly see if a waste available can be used as an aggregate or a supplementary cementitious material or a filler or an alternative for concrete construction. And then we see how we process it. We take care of the beneficiation, improvement of the waste so that it can be used in construction, and finally see how it can be put into concrete and the infrastructure. So some waste that we've already started looking at in other than concrete waste are recycled asphalt pavement. This Surender is particularly looking at it, where we have gone from distressed flexible pavements to wrap concrete pavements, and this has been done at the site. And we are looking at other ways also, like coir, coconut coir, gray water. So all these we are trying out to see how it can be used in construction. Within this initiative, this present project that we are talking about, concluding sort of today with Brunel University, gives us the framework for a high value added zero waste recycling concrete, originating or based on construction and demolition waste. And as was discussed, the group from the UK side is headed by Xiaoming Zhu, or Michael as we call him, with other team members. And our team has Dr. Piyush Chaunsali and Dr. Surinder Singh, along with Rohit, Ram, and Anusha, some of whom will be speaking today, and you will hear from them. So the proposed work, I think Michael will discuss more about the project, has three major headings: material processing, where we primarily are looking at thermomechanical beneficiation of demolished concrete to make it as good as possible to put into concrete. We characterize this material on the raw material side and the concrete side. We try to see how much of this can be recycled into concrete. We are also looking at CO2 sequestration. And then the idea is to have a network of recycling facilities, and finally life cycle assessment, which will be also discussed in this workshop. Okay. So this is to set the stage for the workshop, introduce what our group and that of Michael, we have been collaborating. And now I'll let Michael take over and tell you specifically about the project and what we've been able to achieve. Thank you very much. Over to you, Michael.
Thank you, President Goto. Let me just find my screen. Okay, so okay, you see my shared screen with the
Yes.
slideshow.
Yes.
Okay, thank you, President Gato, and very nice and introduction of your work and IIT and Madrid and also the project. And it's been great pleasure in the last 2 years working with you and your team.
Michael, we can see the presenter view. Maybe if you can close the presenter view and go to screen view, it will be good. You can do it by clicking on the 3 dots.
点一下右键，然后
You can see the 3 dots below your screen.
hide
Yeah.
presenter view, hide presenter view.
Yeah,
You
you
can see
click on the
right
3
click.
dots.
In
刚才
my
点右键。
screen,
Yeah, and you go to full screen now.
is that full screen now?
Yes.
那
No,
你
no,
点一下
it's
右
going.
键，点一下
See,
右键。
you-
刚才你有一个在那个
You
产
have
品
to
里
go
面
to
点一下
the
右键。
You have to go to the 3 dots that you see. If you go back to the other screen.
In my screen, I see it's a presenter view, but let me see.
Okay.
Slideshow. That's slideshow.
对，没错。
I'll guide him. So yeah, now you
Yeah.
can share your screen. So Professor Michael, you can see if you go towards the left, you have a pen mark. After the pen mark, you have to again come back there. Yeah. You can run your slides. When you run your slide, then only it will
先
be
播放，
coming.
先播放。
Okay. Let's okay then.
Yes.
然后
Okay.
你那个
Then
鼠
you
标
go
放到
to
左边，
yes.
哎
Yes.
hide
Yes,
hide
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 presenter view. Hide presenter
Okay.
view. Yeah.
Is now
Yes.
Is that
Now
what-
you go to full screen.
okay? No full screen.
No.
something wrong.
If this is okay, it's fine.
Then it's good. Yeah.
Yeah.
就这样，
If you
就这
can
样放
click
吧，
that.
就这样讲。
Yeah, click that, Michael.
Okay, is it okay now? Because I see my
No,
full screen.
Okay.
There's no shit.
Well, if you can increase the size of your screen, this also could be okay. We can see it still in the edit mode. No, yeah. Okay, this may be good enough.
Okay.
Yeah.
I thought okay, maybe the screen share is not stop share. Let's see.
Okay.
Sorry, let's share screen. Screen 1, screen 2. Which one? Let me try. Is that full screen?
Yeah.
This one?
Maybe
Okay.
you can hear the second screen.
Okay, this one.
Oh,
Is that
yes.
full-
Now this is okay.
Yes, perfect. Perfect.
Okay. Thank you for guiding me. Okay, it's my great pleasure. I think the last 2 years working with and my colleague and IIT Madrid, led by Professor Goto, and we actually learned quite a lot from this big team, and with a good reputation, a world-leading reputation, and the successful project is largely down to them. I have to credit this, express our appreciation to them, and obviously that's in the last 2 years, and some of the activities we planned, such as exchange student staff, has been jeopardized by the COVID, but nevertheless we have some achievement. Okay, so the project started and is an initiative so-called UK IEI. It's UK India education research initiative, and that's a phase 3, I think, and which cover 2016 to 2021. The time we think about that, one of the topic is waste and valorization and urbanization. So we think about that and to submit a proposal. Then I contact IIT and Madrid. I know they are the best and in India, but no doubt. And so I receive a welcome and from the teams at IIT. Then we eventually submit the proposal, and we have a good kind of collaboration during the proposal stage. And it was successful. We started the project in April 2019. So the project is funded from British Council and also Indian Department of should be Department of Science Technology. Sorry, there's something wrong here. I'd like to see that some challenging we're facing, and not just before we submit a proposal, some challenge we're still facing. Recently, we have some proposal to the European Commission, Horizon Europe, and participate with some proposal addressing that the challenge for valorization of construction demolition waste. And it is by volume, it's the heaviest volume, most voluminous waste stream generated in the EU. And it is estimated around 875 million tons in 2018, and in the EU 27 countries, and at the time UK is included at the time. And it comes to 25 to 30% of solid waste and generate in EU. EU have legislation. They set up the target, so-called 70% material recovery from CDW by 2030. And most of the target has been, most of the country has achieved the target and by now. And so the new and target now is 80%. And but even that's the country who claim they have achieved the 70% material recovery target, most of them is done recycling, okay, for low grade purpose, like for the road basement materials. It's not been highly or fully extract the value from CDW. Okay, so the reuse is still low. It's still low. Okay, so this is the challenge we are facing, and not facing just by UK, India, and also by Europe. Okay. So we do need a circular approach, and to deal with the CDW recycling, and we want to extract values from the CDW, so turn the waste into valuable materials. Okay, that's the target, or this is the vision we have when we submit the proposal. So the objectives, Professor Gato just very well summarized in one of his slides. Okay, so the ultimate objective is that we need to recycle and reduce CDW concrete. Okay, we want to recycle and into the individual components such as aggregate, coarse aggregate, and fine aggregate, which are sand, and also cementitious paste and powder, and something like could be the residues, which could difficult to be fully recycled to individual component, which then can be downcycled to a base material for road construction. And overall, and the key things in the center is a circular economy approach for CDW recycling. Okay, the three specific objectives. One is obviously is trying to develop and optimize and improve technique for recycling and the high value raw materials or individual component from CDW concrete. Okay? And the second one, we realize that is a potential through carbonation and from recycled hydrate cement paste to absorb carbon. And today I think that's some of the research presentation will about this research. Okay? And of course, and in order to promote the technology, and with not just sitting in doing the lab, okay, we want that to optimize the supply chain. So industry concerned sector realize there's a great potential. There's a business mode there. So that's why we have proposed to optimize the supply chain for CDW and based on life cycle assessment analysis. Okay, and we have taken a case study in the UK and India, particularly in India. Our AI team has done a very good model on the supply chain of CDW. And in the presentation from Professor Gato, you can see that they have already put some technology in the test bed, and they have some very large scale application, which is very encouraging. So the main concept of the project, I would like to use this diagram showing that. Okay, so in the center is circular construction. Okay, and we didn't touch for selection collection waste. Okay, that for the upstream in this project, but this is something, and obviously it could be very interesting topic and to selection. Okay, so ways of selection, obviously, and waste materials. Okay? We're trying to, and the work can do could be in the automation to select and waste, and use robotic, use the sensor to separate different types of waste. Okay? And the waste need to be sorted and clean on site, and then we send to the waste and recycling plant, and which is a well-controlled facility and the environment. Okay? And we try to separate into individual components, as I just mentioned. Okay? And then this recycled materials, individual component, will fit in the as a feeding materials to the new manufacturing production line. Mainly goes to construction again, Okay, so obviously some of the work should be do is trying to get the quality control, and in Europe get a CE market. Okay, CE mark. This is obviously and very challenging when work with on waste materials, but this is something it should be do in order to promote the technology, in order to bring technology closer to market, or even and largely apply in market. Okay, obviously we need to engage with the policymakers, and we need to already engage in the regulators. Okay, and we need to change people's mindset. Okay, mindset how they accept the use the waste materials or secondary materials. Okay, that's in reality human science and activities. And we just want to see some outcome from this project. Okay, so one of the things, and which is a nicely picture done by our colleague from IIT, and they're showing the diagram on the concept of the whole recycling and process for concrete into individual component. Okay, from the previous presentation from Professor Gato, you can see that they are really have put in a large scale test bed already in India, which is very encouraging. Okay, bring the technology a step closer to market. Okay. And you can see that after this compared with the aggregate, okay, recycled from waste concrete, compared with the virgin aggregate, okay, after and treatment through a chemical and thermochemical treatment, we can get the aggregate, which is a property which is comparable to the virgin aggregate, and in some aspect even better than the virgin aggregate. And you see that this some of the plant in India, they have a mobile and collection and waste concrete recycling and vehicle, and they have a large scale recycling on site, and obviously this can serve to the high speed and faster urbanization in India. I think that's a great potential, and to many other countries as well. Okay, and one of the other, as mentioned, the second target is trying to use recycled hydrated cement paste to absorb carbon. In this regard, and my team member, Dr. Shaoxin Yuan, he has done some research in these areas, and today he may touch on his some research, and which obviously at the moment is still in the pilot scale, hasn't been really largely put in the industrial scale, but it goes showing that great potential. So on top of this, obviously the technical achievement, okay, and the project itself, this kind of funding itself is facilitate the exchange of staff and students to build a network and to exchange and research ideas and also exchange culture and to experience that the people in different cultures. I'm glad to see that we have received a visit from our IIT team, and my team also visit IIT in Qinghai. And we should have more such kind of visit and workshop and in-person and kind of meeting. But unfortunately, it's been largely jeopardized by the 2 years long COVID. Okay, so some opinion shown here. The top right corner is that the first visit from our team, IIT team, to Brunei, and some of you can see the face and today in this team's Zoom meeting. And the top left corner is that the team with the second concrete plant in the UK, and the top right corner is that my team visit India, and together with our partner in India, they visit a recycling plant somewhere in Chennai. Okay, I think that's all my presentation, and again, I would like to thank my partners and at IIT Madrid, especially Professor Gato and his team. And I have to say that the success of the project is largely down to you and your leadership and your team. And thank you very much.
Thank you.
Thank you, Michael. For the interest of the students, I like to let them know that Professor Michael is also the head of the Department of Civil and Environmental Engineering at Brunel University, London. So thank you, Professor Zhao. Now I would like to invite Dr. Peng-Kun Ho, who is a research fellow at Brunel University, London, and today he'll be giving a research talk on nanosilica engineering of super sulfated cement. Dr. Ho, if you can, you have already started sharing your screen.
Yeah. So I can get started now, huh?
Yes, sure.
Okay. Yeah.
Yes,
Hi, everyone.
it is visible.
It's my great honor to be here to give a presentation on nanosilica engineering of super sulfated cement. It's try to use as much as SCM as possible. So there will be 4 parts: the background of using SCMs and the problems we're encountering. Nowadays, that CO2 emission becomes a great concern in cement industry. People try to use a lot of SCMs, these luminate silicate SCMs like flash, GGBS, to potentially reduce CO2 emission. In China, for example, in 2020, used over 700 million tons of SCMs. All these SCMs are characterized in high content of silicon oxide and aluminum oxide. But when we see the development or the trend of using these SCMs, we can see that we are facing the problem of low quality. The shortage supply of GGBS in European, in every country, and SCMs remaining in large quantity are actually low in reactivity. So this can be more easily seen from the quality development of GGBS in China. So this picture shows a statistic research study of the GGBS used in the last 75 years. So we can see that the reactive content, such as aluminum oxide and calcium oxide, decrease in the last 25 years. So there's a great concern on how to improve the reactivity of aluminate silicate SCMs used in cement concrete to make this industry more sustainable. So in the last 10 to 20 years, bunches of researches have been conducted on using nanoparticles such as nanosilica to improve the properties of cementitious materials. So when we look at the production of the nanosilica, generally it's 3 steps: the hydrolysis of the precursor such as TOS, and then the alcohol condensation and the water condensation happen, and then the silica dioxide molecules grow together, forming dimer, trimer, and the nanosilica, which is like less than 100 nanometers. So when we look at this nanoparticle, it is characterized of full of hydroxyl group outside, and it is actually negatively charged. When being added into cementitious materials, these nanoparticles act as seeds for cement hydration. And this has been proven by studying the C3S or the silicate systems. Then the hydration can be shown to be accelerated. And also many work has been conducted to study its acceleration effect on OPC. Actually, for OPC is an average acceleration effect, meaning the silicate phase, aluminum phase, and other phases. So there comes the question, what's the specific effect of nanosilica on aluminum phase? To do that, we designed a system consisting of C3A and 30% of gypsum, which is actually polysulfated. And we can see two distinct peaks. Q1 representing the hydration of C3A with gypsum forming AFT. And then Q2 is the after depletion of the gypsum, the transformation of attringite to AFM. So how will be the effect after addition of nanosilica? It's astonishing to see that this addition of nanoparticles retards the hydration of aluminum phase. And this retardation can be confirmed by the phase assemblage transformation. I mean, the formation of attringite or the transformation to AFM. So this phenomenon can also be found when the system be changed from the polysulfated system to a properly sulfated system, which, for example, 0.662 is the percentage of the calcium sulfate, that's gypsum, to C3A, which is the case in OPC. So by quantitative analysis, by the analysis of the C3A gypsum and the tringite, the characteristic phases in this system, the same phenomenon, that is retardation of aluminate phase by nanosilica, can be confirmed. Regarding the mechanisms, actually we can get some hints from the effect of gypsum on the retarding of C3A. So when the gypsum was added into C3A system, people recently, I think it is confirmed that the calcium to sulfate a complex form, which can be absorbed onto the positively charged C3A particle surface. And this kind of absorption will actually lead to the reduction of the potential of the C3A particles, and also blocks the dissolution of the C3A particle, which will finally reduce the hydration of the C3A. And when we further add nanosilica into the particle, into the system, we can see a further reduction of the potential can be observed. This, actually makes us to think whether nanoparticle can act as kind of the gypsum in the C3A system. So to do that, we make an observation of the C3A plus gypsum plus nanoparticle system. We can clearly see that nanosilica clusters were absorbed onto the C3A particle surface. And actually, this kind of structure, you can see like a stalagmite and stalactite on the C3 particle is formed by the bridging of the nanoparticles, which is negatively charged, by the positively charged calcium ions, then forming the stalagmite structure. So from this, we can conclude that the negatively charged nanosilica particle can be absorbed on the positively charged C3A aluminum phase surface, which will then hinder the aluminum reaction. So then just as the gypsum does. So here comes the question: how to take advantage of these two effects? The effects of nanosilica on the acceleration of the silica reaction, and also the retardation effect on aluminum reaction. So can we find an ideal system to take both characteristics? So which is cannot happen in OPC because of what? Because of so much less aluminum phase, like 4% in OPC. So can we think of using these characteristics in high aluminate system, for example, in the like in the SCM, high volume SCM replaced system? So if this can be used, then can these two characteristics be used to improve the low performance of the high volume SCM systems? So to verify that, we investigate the performance of nanoparticle on supersulfated cement. So this kind of cement consists of 75 to 85% of GGBS, and 10 to 20 gypsum, and 1 to 5 just clinker. And the hydration products is characterized by the large volume of attringite, as you can see here, and also the CSA gel formed by slag hydration. But a problem of this system is that the slag reaction rate is low, which will result in the low strength gain in the early and the later age. But it is high in aluminum phase, and so we can let's see whether nanoparticle can behave to improve the strength, or how will it perform on the carbonation resistance and the free sol resistance, which is actually the shortages of the SSC system. So to do that, we made the proportions like 2 dosage of gypsum, 4 and 10%, and we added 3% of nanosilica, and then the GGBS we used has the aluminum phase of about 17%, and then to do the hydration and then the mechanical testing. So let's first see the compressed strength. With the addition of nanosilica, for example, 3%, we can see that it can potentially increase the compressed strength of SSC. For example, at 28 and 90 days, the compressed strength can almost double. And then when we analyze the hydration degree of GGBS, it can be found that the hydration of GGBS can be potentially increased by nanosilica. So actually, this mechanical performance can be researched by the more macro analysis. For example, the CSH gel. This analysis, we can see after the 3% of nanosilica addition, the CSA gel formation greatly increased. As you can see here, even doubled at 90 days. So it's a positive effect on CSH formation. That's acceleration effect of nanosilica. But there's also a reduction of the attringite formation. That is the retardation actually found in previous research. So when we make a calculation of the CSH and its proportion to tringite, we can see that the gel to crystal portion, rate increases with the addition of nanosilica. So actually, these kind of features can be more easily found from the SEM image. You can see from here, without nanosilica, it's very porous, and the fine crystals, needles, which is the tringite, and a lot of pores, of course. Actually, these are capillary pores. But with the addition of 3% of nanosilica, we can see that the structure can be greatly densified. And then you can see the critical pore diameter shifted from 72 nanometer to less than to about 6.5 nanometers, which is actually the gel pores. So with this, we can draw a this kind of picture showing how the nanosilica affected the microstructures. The previously porous crystal, the AFT and the CSA gel structure can be turned into a very compacted, more CSA gel and less AFT structure. And actually, I want to say that AFT morphology has also been changed. Then we did the focused ion beam SEM tests. From these, we can more clearly see how the microstructure be changed with the addition of nanosilica. So can be further used to verify the structure model before and after nanosilica addition. So we can see the increase of CSGL, the decrease of tringite, and decrease of AFT to gel. I think I made a mistake, right? So decrease of tringite to gel ratio. How will these features affect the mechanical property? So we did a regulation study showing that the reaction degree of flak, that is the CSA gel amount, and the volume ratio of a tringite to gel are closely related to the strengths. So this will be can be well explained why the nanosilica improved the strength and how the structure was modified and how the strength can be improved by nanosilica. So with this, I would like to conclude my presentation that nanosilica accelerates silicate phase hydration, but retards aluminate phase hydration. And these features can be well taken advantage of in high aluminate content blends, such as the lots of SEMs with different aluminate sources. So that's all my presentation. Thank you.
Thank you, Dr. Now I'll request Mr. Rohit Prajapati, who's currently pursuing his PhD in the Department of Civil Engineering at IIT Madras, to give a brief talk on the topic use of thermomechanical beneficiation for recycling of concrete waste.
Thank you, sir. Can you see my screen?
Yes, I can see this.
Okay. So I'll be presenting the part on from the first objective of material processing, where we have optimized this thermomechanical beneficiation technique. And so I'll be starting with the background, and then we'll have some slides on how did we optimize the beneficiation technique, and then some concrete results. So I'll start with the background. So in India, we have a lot of problem related to C&D waste disposal, and other side you have a huge demand of aggregates. So according to a report, India produces more than 700 million tons of C&D waste every year, and the current recycling capacity is only 1.2 million tons, which is less than 1%. So this demand of aggregates can be addressed through producing the recycle aggregates from the C&D waste. So all we know that construction demolition waste are the materials that are produced in the process of new construction, remodeling, repair and maintenance of structures, and also demolition of the old structures. So out of the total C&D waste, almost one fourth part of C&D waste in India is concrete, and in developed countries it could be up to 70 to 80%. But if you see the maximum replacement of coarse aggregate in many standards, it is 100% allowed, but only in lean concrete or non-structural application, whereas only 20 to 25% is allowed in reinforced concrete application due to the inferior properties of recycle aggregates. So what is the difference, basic difference between natural aggregates and recycle aggregates? We have attached mortar on the surface of the aggregate. This attached mortar is responsible for high water absorption, could be 4 to 5 times high, and lower mechanical strength. And if you replace natural aggregate with the recycle aggregate, the strength could reduce up to 30%, and there could be other serious problem related to the durability as well. So when you put this aggregates in the concrete, so in normal concrete we usually have one type of ITZs or the interfacial transition zones, but in recycle aggregate concrete you have multiple ITZs. So the old ITZ between old mortar and aggregate, and there could be new ITZ which is formed with the new cement mortar and the recycle aggregates. So we know that this ITZs are weakest zone, so that influence of ITZ is magnified in case of recycle aggregate concrete due to the complex or multiple ITZ presence. And what are the main failure modes if you talk about recycle aggregate concrete? So there are 5 type of failure modes. First is the crack could pass through the new mortar, or it could go through the ITZ between old mortar and new mortar, and it could pass through the old mortar itself and the old ITZ, or sometime it can pass through the aggregate itself. So out of these 5 failure modes, 2 failure modes, 3 and 4, which is through old adhered mortar and between the old ITZ, are more common. So there are methods to treat the aggregates, so which could be classified in 2 types of methods. One is removal of the attached mortar. So we can use mechanical, chemical treatments, microwave, and conventional heating or ultrasonic cleaning. And there are other methods which are focused on modifying the surface of the aggregate using fine materials or chemicals. So this presentation will be focusing on the thermal treatment or the thermomechanical beneficiation technique. So we have got aggregates, old concrete from a 15-year-old building, and then we did the side reduction and homogenization, and then we heat these concrete pieces to in a electric furnace, and then after cooling it is milled and scrubbed, and then you get this 3 type of products, which are coarse aggregate, fine aggregate, and the concrete fines. So what is the acceptance criteria, or how did we optimize this process? So first we set an acceptance criteria for process and products. So process is the thermomechanical beneficiation, and the products are the produced recycle aggregate. So we looked at a few stringent standards, and then we pulled out some values for dry density and water absorption, which are the key critical properties for recycle aggregate and have direct relationship with the amount of adhered mortar on the RCA. So from that we got the parameters for quality of recycled products, so which is in terms of water absorption and dry density. And we have 2 parameters for process efficiency, the total yield and the amount of concrete fines. So first let us understand what is the parameters for the efficiency of the process. So here I have plotted the weight fraction of different size of particles. So first box you have concrete fines, which is the particle less than 0.3 mm, and then you have fine aggregate, coarse aggregate, and the last box is particles about 20 size, or you can say just unprocessed material. So the concrete fines will be the amount of particle less than 300 micron, and then concrete fines together with coarse and fine will be considered as the total yield. So the total yield should be more than 90%, and this concrete fine should be more than 20%. So the heating temperature, duration, and the mechanical scrubbing process was optimized in 2 phases. So first phase, we have fixed the heating time to 2 hours, and then we have varied the temperature from 350 to 500 degrees C, and we have 2 types of milling operations, with charge and with charge as a steel balls. So with the first phase, we could see that 500 degrees C is sufficient to satisfy the process efficiency parameter and aggregate quality parameter. So this 500 degrees C was optimized here, and then in the next phase, it was fixed, the temperature was fixed, and then we varied the heating time. So from this phase, we could see that even at 60%, 60 minutes is enough to weaken the concrete to produce the acceptable materials. So this is the optimized process where we reduce the size to 50 and then heat it for 1 hour. And then after cooling, it is milled in a milling machine. And then you get these three products, which is coarse, fine aggregate, and concrete fines. So just to show you some properties, we have compared the aggregates with pristine granite aggregates, laboratory jaw crust aggregate, and we also got aggregates from the industry. So you can see that the water absorption is is comparable, and we were able to remove almost all the adhered mortar up to 96%. Similarly, for fine aggregates, we were able to improve the water absorption to almost 6%, which is 40% less than the untreated recycled aggregates. So since we have removed this adhered mortar, so these 2 failure modes were eliminated. Now let us see what happens on the what is the effect of this beneficiation on the concrete properties. So we have 2 series of concrete. In the first RAC, we have volumetrically replaced the coarse pristine aggregate with the beneficiated aggregates, and then the second one we have replaced only fine aggregate. So you can see that even if you replace 100% aggregates, the mechanical properties or the compressive strength has not reduced much. And here I have plotted one case where if you use untreated aggregates, it could go down up to 30%. Similarly, in fine aggregate replacement also, we did not find any significant drop. And we also have done other tests such as flexure test and complete stress strain curve. And then we could find that all replacement ratios, we could get the similar performance. We also have done the durability test. One of them I'm just presenting here. We have the oxygen permeability index. So we could see that all replacement have comparable performance. And durability is a big problem in case of recycled aggregate concrete, especially when you use fine RCA. So let's go back to the methods of removal of adhered mortar. So I've compared these 4 methods. So you can see that conventional heating or scrubbing, the thermomechanical treatment yields best improvement in water absorption and best efficiency in removal of adhered mortar. So you can get the high quality aggregates. Hello. Yeah. So you can get the best quality aggregates, but the energy consumption is high. You can see that we have to heat the concrete to 500 degrees C. So we have tried to change the heating mode and try utilizing the solar energy, concentrated solar energy. So we have transported the concrete to India One solar thermal power plant in north of India. And this is the disk concentrator. And then you can see there is one receiver, small receiver here. So we loaded this material and we have monitored the temperature, and we have tried to use the same optimized parameters what we were using in the conventional or electric furnace heating. So the sunlight is concentrated and it is focused on this receiver, and you have the material inside, and you can cover it with the glass cover to reduce the convection losses. So the assessment of recyclability was done in the similar way. So we have the process efficiency. So again, you have this first box where EF, electrical furnace, and then OS are the trials from the solar heating. So you can see that it yields almost comparable products. And just to highlight the effect of heating, you have this last trial, BM, which is just ball milling. So if you don't heat the concrete, then your yield is very less. And then aggregates, what you produce will not be free from the dead mortar. Similarly, so here you can see the water absorption and dry density. So this black line is the acceptance criteria. So you can see the JC is the jaw crushed aggregates. So these are having higher water absorption, and then all this OS trials from the solar heating and EF from electrical heating are satisfying the acceptance criteria in case of water absorption and dry density as well. So to summarize the results, so high quality RCA can be produced using this thermomechanical beneficiation techniques, and the properties could have comparable performance as the pristine aggregates. And the benefited RCA did not affect the mechanical property, and more importantly, the durability. It was found similar even at 100% or complete replacement. And the preliminary results shows that solar heating setup, all the trials were robust, and there is a possibility that it could be used in applications at high scale. So in the end, I would like to acknowledge the financial support from UKI DST and UKI SEED and Brahma Kumari's World Renewable Spiritual Trust at Mount Abu for allowing us to do some experiments at the India One solar plant. Thank you.
Thank you, Rohit. Now we have come to the end of session 1. Now we'll be starting with session 2, which is on policy, C&D waste management, and life cycle assessment. So we have our first speaker, Mr. Ram VG, who will be, who is a PhD research scholar at IIT Madras. And today he'll be giving a brief talk on strategies, pathways to enhance construction demolition waste recovery through recycling projects. So I request Ram to share his screen. Okay. Ram, you have to unmute yourself. Ram, can you hear me? You have already shared your entire screen. Now, yeah.
I'm sorry,
now,
yeah,
yeah.
I think,
yeah.
yeah. Can you can hear me, right?
Yes, yes. Now I can hear you.
I just share my screen.
I can see your entire screen now. So yeah, you can open your PPT.
So, did the slideshow come in?
For me, it's a green screen. The full green screen. I don't know what. Rohit, what about you? I think it is slowly coming.
Yeah.
It is taking some time. I think it's of very high resolution, maybe.
Okay. So I'm not sure, there's some internet connectivity issue. Did the screen come up?
Not for me. I can see only 1/4 of the screen.
I'll just stop the screen share and I can share. Did it work?
Now, yeah, it's fine. You can go ahead, Ram.
Thank you so much, Dr. Surendra. A warm welcome to everybody. And today I'm going to talk about strategic pathways to support C&D waste recycling. Dr. Surendra, I hope the slide is changing, right?
It's taking a little bit of time, but yeah, now I can see your second slide also.
Okay.
Go ahead.
So we all might be familiar with the 17 Sustainable Development Goals, where today what we're really interested in is this SDG 11, the Sustainable Cities and Communities. That is, we have set an ambitious target of housing for all by 2030. And why did we choose it? Because there's a lot of housing shortages that exist globally. The pie chart that you see on the screen, it's showing you that over 1 billion population people are actually living in slums or in substandard conditions, and a major chunk of them is actually in Asia and Africa. And that's not in the story, because the demand is continuously rising. For example, today almost half of humanity is living in cities, and it is expected to reach about 5 billion by 2030, and about 70% of the world's population may live in cities by 2050. So what that tells us is we need to start building housing and other urban infrastructure right now. Of course, the growth requires the resources, right? So right now, the domestic material consumption or the material footprint is somewhere about has risen from 8.7 tons per capita in 2000 to 12.2 tons per capita in 2017. So what this graph is masking is the wide disparity that exists between different economies. For instance, well-developed economies in Europe and North America have actually a material footprint of about 20 to 25 tons per capita. On the other hand, Asia and Latin America, they have a material footprint somewhere about 10 tons per capita, which is around about the world's average. And Africa has a material footprint of about 3 tons per capita. Thus, people have actually found out that human development index is highly correlated with material footprint. And what that does tell us is, if we are to actually achieve a good standard of urban and housing infrastructure, and we have to probably reach a material footprint of about 20 to 25 tons per capita at the overall scale, and that roughly translates to somewhere about 180 to 200 billion tons of domestic consumption by the end of 2050, where we probably reach somewhere about 9 to 10 billion population in the world. Right. So that has consequences, which means we are going to exploit our resources at a very, very rapid pace, and natural resources are going to get depleted. And more importantly, there is going to be supply shortages in the short and medium term, because a lot of the resources that we need for our infrastructure building and development is not just conveniently sitting around the urban settlements, but it is also being located in very different locations. So we have to go far and fetch the resources and bring it back for our development. And that is going to add a lot of pollution, dust, noise, and other environmental impacts as well. On the other hand, we have industry is actually wasting a lot of resources. For example, India is generating somewhere about 400 to 700 million tons per year, and right away on that to 1 billion tons of C&D waste generation in China. And a major chunk of them, that is concrete, bricks, tiles, and soil, are just disposed in landfills, or they just disposed randomly in all places in the city. So we clearly have a problem of material wastages on one hand and material shortages on the other hand, and industry is clearly reluctant to perform recycling, which we do not see, right? And which really gives an idea that there are a lot of barriers to recycling. For example, there are several barriers reported in the literature. For example, lack of precise and detailed regulations. There is also ineffective regulations, or they are not sorting the waste on site, and therefore gives inferior quality of recyclable waste to produce. There's also a lot of illegal disposal, which is actually affecting the collection and transportation of waste to the recycling facilities. Or we also have a lot of orthogonal priorities among the stakeholders, where they do not prefer recycling and they just want to be disposing of this waste. So there are a lot of cognitive barriers as well. So how are we going to address all these barriers? Because we clearly know recycling has to be preferred and has to be pushed in the system. So the literature have actually talked about a lot of mitigating strategies, ranging from active bans on landfilling to incentives for recycling, to setting up more landfills, mandatory waste management plants. And each of these mitigating strategies have been adopted in different degrees. And I've also actually achieved different degrees of success in those regions. So what is the problem? So if at all, I have to actually improve my recycling rate. So I want to know what combinations of these strategies is actually giving me success so that I can deep dive on such mechanisms and concentrate my effort and push the recycling rate farther up towards the north. And if it is for a country such as India, where we are really starting from scratch, I want to know really some handful of strategy or strategy combinations that is actually contributing to success so that I can just mimic it immediately and get some results at a fast pace. Right? So the focus of my talk is going to be answering the question, what strategy and strategic combinations support successful development and operation of single-use recycling. While the question is clear, we're still not sure how do we achieve it, because if we talk about answering the research question with some of the methods, while we have in the entire research method spectrum, we have quantitative methods on one side, where it is predominantly variable oriented and has a very systematic analysis framework, and therefore is highly accepted. But it has a problem that it requires large data sets. And where are we going to go for large data sets where we are still struggling to find ways in which we can boost recycling, right? So that's ruled out. On the other hand, if you go for qualitative methods, that is predominantly case oriented and it gives a contextual analysis, but it has to be on small data sets, because doing large in-depth ethnographic studies in various countries and regions is not really going to be effective, and it's not going to be easy task. So, however, there are some advantages that I want to be mixed. For example, in qualitative methods, what it really gives is a good contextual analysis. For example, it preserves the multiple causal pathways of combinations that actually contribute to success, because it's not just one combination that will give me success in recycling. Right? So multiple combinations possible. So which kind of analysis is not really possible with quantitative methods, which are predominantly deterministic. On the other hand, I also want to have the benefits of quantitative methods, such as systematic framework, and I want to combine, and therefore I'm going to choose a method that falls somewhere in the middle of the research method spectrum, which is qualitative comparative analysis, which kind of preserves the contextual causal pathways that exist in the system, as well as it gives me a robust framework to analyze the data. Therefore, it faces less criticism towards generalizability and repeatability as well. So how does it method work? For example, so we have to define a research objective. So in our case, we really want to correlate success of research initiatives with the combinations. Right? So we choose the conditions or hypotheses or strategies that actually contribute to the success of research initiatives. We also want to define our success metric, or how are we going to define whether this is success or failure. And we also have to choose cases in such a way that we actually have cases that depict both success as well as failure in terms of outcomes. And it also has a good heterogeneity of conditions that have been implemented so that we get a good analysis of the data. Then we have to then convert our qualitative data into Boolean data, because QCM method uses principles of Boolean algebra, and then we can perform our analysis, and then we can interpret. So I'll just give you a brief illustration of how this QCM method works. It can be easily replicated. So let's assume that we have a construction project where we have productivity targets to be achieved. And I want to actually know if I want to have which crews or labor crews can actually be integrated into my existing labor crew, and how will they perform. I take a decision on them. Right? So this gives me the conditions, that is crew A, crew B, crew C, and crew D. There are 4 different conditions I want to test, and how do they correlate with my productivity targets. And I'm going to actually observe for 16 weeks, which will form my cases. And say, for example, in the first week, I'm not going to put any of those crews in my system, and I'm going to see whether I have achieved productivity or not. In my hypothetical data, let's assume that we have achieved the productivity target, right? So I'm just writing it as 1. On the other hand, because of the absence of crews that I'm putting in the system, I'm just putting them as 0. For week 2, I'm just introducing crew D in the system, and I'm eliminating A, B, and C. And therefore, I'm just putting 1 and D, and assuming productivity target has been achieved, then we have quoted as 1. So similarly, I look at various combinations of crews in the system, and then I'm measuring productivity and see if my productivity targets have been met, I will put them as 1. If my productivity target is not met, then I will put them as 0. So now I want to really understand what kind of combinations of fixed screws in my system actually giving me or helping me achieve the productivity target. So let's say in B10, it is I am writing the presence of a screw as capital let's say, absence a small letter, small c, and capital D. So P, which is 1, success is equal to A, B, C, D. Similarly, for all of the 4 success instances, I am going to write them and depict them in an equation form like this. Okay, so now this forms my complex solution. Like multiple combinations of these are also giving me a success. Right? So now I want to simplify this and see if I can make some meaningful inferences out of this. So there is a principle called Boolean minimization, which actually talks about if any one of your conditions, the presence or absence, does not differ your outcome, then it can be eliminated in the simplified solution. For example, if you look at this A, B, C, D and A, B, C, capital D, the presence of D and the absence of D really did not change their outcome, which is P, that is 1. Therefore, I am going to eliminate D and just denote them as A, B, C. Similarly, if you look at the next terms, the presence and absence of A really did not change the outcome, and therefore I'm going to denote both of them as B, C, D. Similarly, the third, the presence and absence of B is really did not change the outcome, and therefore I'm just going to represent them as C. So now we have achieved 1 degree of simplification, which is from this complex notation we have reached now here. So now how do we go further? So there is something called prime implicant chart, where I'm going to write the complex part in the columns broken down, and the simplified first order solution is the rows, and I'm just noting down. For example, ABC capital D is represented by ABC. Therefore, I'm just putting an X here. So this ABC is actually able to represent 2 parts of the complex solution. Similarly, BCD is representing these 2 parts. The third row is capital A small c D represents the third and fourth part. If you look at this prime implicant chart, your ABC is able to represent half of your complicated solution, and the third row is capital A small c D is able to represent the second half of your complicated solution. Thus, together ABC and third row is able to represent your entire complex solution, and therefore it can be simplified in this manner. Or if you want to simplify further, you can probably then take CR out, and so therefore it's AD plus AD. So how do we infer the solution? For example, C is basically the absence of crew C. So if I want to actually achieve my productivity target, I should not employ crew C in my projects. That's kind of become a necessary condition because it is available in both of the parsimony solutions. On the other hand, but that's not sufficient condition because I mean, it's just necessary. But in order to make it sufficient, you will have to negate A and B. That is, crew A and crew B also should not be employed, or you should not employ C and you should employ A and B. That is the kind of simplification we're able to achieve from 16 cases and 4 variables to just 2 simple pathways. Similarly, in our case now, we want to really identify what are the conditions that actually contributes to recycling. Right? So I did a systematic search of literature and using these listings, and we have 300 articles, and they were coded underline. And second other things are over 32 strategies that contribute to recycling initiatives are found, and they were grouped under 10 strategies, which are taxes, subsidy, R&D programs, restoration plans, training schemes, disposal, voluntary, demonstration projects, waste exchange platforms, and non-landfills. These are sources and the frequency in which they are appeared in the literature. So now we are able to systematically retrieve what conditions contribute to recycling initiative, but we just want to know what are the pathways that can actually contribute to success. So therefore, what is a success metric? So I'm going to just take the European Framework Directive, which talks about total percentage of recycled quantity or total waste generation as my metric. And I'm going to fix a criteria, so at least 50% of the waste we recycle will be coded as success, and anything less than 50% will be coded as failure. So I just want to understand what differentiates or what combination strategies differentiates a high recycle rate in some places with low recycle rates in other places. So we have taken outcome conditions, and now we have to choose cases carefully such that we have heterogeneity of conditions as well as outcomes. So from the reports published by the function, we have detailed histories of individual member states. So we have taken 14 member states for this study, where 7 of them have actually have a high recycling rate, say above 40%. Some of them even achieve 90%, and some of them are actually have very less, even around 5 to 10%. So we have chosen the year of data specifically in such a way that this heterogeneity in terms of achievement of success in growth rates have come up. So now we have selected proper cases, the conditions and outcomes, and now all we have to do is convert the qualitative data into a good truth table, just like we discussed in the illustration. So this is the coding rubrics where some of the variables, say if they are present, we'll be coding them as 1. If they are not present, we'll be coding them as 0. But some of the variables such as R&D programs, demonstration programs, for example, some member states have actually done about more than 20, 30 pilot programs. So we want to differentiate between extensive implementation of such programs and several and few and none. So we also have some of the variables of 0, 1, and 2. So that's why I'm going to take a multi-value QCA framework to analyze this. And so now we can see there are about 10 different strategies or conditions that are hypothesized to affect success of recycling initiatives. And we have about 14 cases that is where we have observed the combinations that we implemented. And depending on the metric that we have chosen, each of them has been coded depending on whether they have a high recycling rate or a low recycling rate. So because we have about 10 variables and 14 cases, it's going to be 14 equations. Solving manually is not going to be easy. We want to take the help of software, which is Spanner, for this MUQC analysis. And once you plug in the data and you analyze it, we are able to simplify the complex 14 equations into just 2 simple pathways. For example, how do we integrate? This voluntary agreements plus tax and subsidy forms one of your parsimony solution, or voluntary agreements and subsidy and extensive R&D form another part of your solution. So thus, we are able to reduce a complex solution from putting equations to just 2 strategic pathways. How does this compare with literature? Of course, literature have actually talked about charges and tax and R&D and incentives in terms of green product labels. However, there is not much attention being given to voluntary agreements as an important criteria. However, we have found voluntary agreements to be an important criteria in our strategic pathways, and therefore that is probably one of the counterintuitive findings that we have been seeing. Of course, VAs have also been extensively used in paper and packaging recycling. However, we also posit that it can play a huge role in concrete recycling as well. So takeaways. So what strategies and subject combinations support successful development and operation of recycling? Towards voluntary agreements, in addition to taxes and subsidy, or taxes and extension and programs. And we also demonstrated that QCA could be an useful approach to analyze causal combinations using principles of Boolean algebra. I would like to acknowledge BST Vicari for the grant, as well as UKC and MHRD. Thank you for your attention.
Thank you, Mr. Ram. Now I request Ms. Anusha Basavas, who is a PhD research scholar working with Professor Ravindra Gettu in the Department of Civil Engineering at IIT Madras. She will be talking today on the life cycle assessment framework.
Sir, is my
Yes,
screen
yes.
now?
Yes, Anusha.
Hello,
you can go
everyone.
ahead.
I'm Anusha.
Yes,
I'm a PhD scholar working with Professor Ravindra Gettu in the Department of Civil Engineering, IIT Madras. Hello.
Yes, Anusha, what happened?
Is this some problem, sir?
Earlier it was in the slide screen mode. Now it again came back. So
One
maybe-
second, sir. Yeah, one
Yeah.
second, sir.
you can unshare and share it.
Now, sir?
Now it's okay.
Okay, sorry for the interruption. So the topic for today's presentation is sustainability framework for concrete systems with recycled aggregates. So when we look at life cycle of concrete, we see that there are several life cycle phases, starting off with cradle, where raw materials like cement and aggregates are being produced and transported for concrete production, and there will be electricity which is produced and be used in all life cycle phases. And all these materials which are produced will be transported and concrete will be produced, and it will be later placed into the structure. So we can use either 3D printing or precast elements or different technologies to place this concrete into the system. Once this concrete is intact, it will go through the service life, where it will be exposed to different environmental, and it has to resist chloride, sulfates, carbonation, etc. So there might be repair and maintenance phase, where the service life of the structure will be extended, and at the end of life there will be deconstruction or demolition, where the waste materials will be disposed of in the grave, or it can be recycled back to be used as a raw material in concrete production. So the cradle is where all the raw materials are being produced, and gate could be the gate of concrete manufacturing plant, or gate of different construction units or the site itself. And that there could be where the materials is disposed of. For doing a sustainability assessment, we have to follow the cradle to cradle life cycle approach, where the performance of the material during its use and after the use also should be considered. So if you look at the different processes that has to be considered in the cradle to cradle approach, we could consider the electricity production and cement production, which could be called ground to gate of the cement plant. So this will help us to calculate the embodied impacts of cement, which can help us to compare the different kinds of cement, or when the production process is changing, or if the materials are changing, we can easily assess the system for that. Or we can include the aggregate production and concrete production, which could be called ground to gate analysis of the concrete production, which basically calculates the embodied impacts of concrete. With this processes in place, we can compare different concretes with different binders, aggregates, and concretes of different strength also can be compared or assessed. So we can include the construction activities in order to calculate the impacts or the analysis of any concrete elements. This could be called ground to gate analysis, which we consider until the construction activities. With the help of these processes, we can compare different technologies and different optimized design strategies as well. So if you look into the other processes that includes the useful life activities during the service life, it can be called ground to gate up to end of life, which can help us to compare different structures with different binders, different service lives, which have different durable concretes. And also it will help us to calculate the impact of repair being done on the total life cycle impacts. We could also include the demolition and deconstruction phase, which could be called cradle to grave, which can help us to calculate the influence of demolition phase on the total life cycle. Or we can also compare different demolition techniques. Or we could do cradle to cradle, which includes all the process that I mentioned before, including the recycling of the waste materials, which would we get from demolition and deconstruction. And we can analyze how much of waste can be reused in the raw material production. So this can help us to calculate the recyclability of the whole structure. So we have to consider all this process to do cradle to cradle, or we can also do gate to gate analysis for each system to understand the influence of each production stage or each phase on the total life cycle impacts. So if you look at the low carbon strategies, there are different strategies that have been followed by cement production or concrete production industry in order to reduce the CO2 emissions. So if you look at the roadmap, there is something called 5C approach we have to follow. We should not only concentrate on each phase, but we should also think of the value chain of concrete in order to reduce a lot of CO2 or the impacts due to its production. So if you look at the last C, that is carbonation, there is a lot of potential in the built environment in order to sequestrate the carbon. If you look at the recycled concrete aggregates or recycled concrete, it has a lot of potential in carbon sequestration. And also we need to understand what is the impact of using the recycled concrete aggregates in the concrete production. What will be the reduction or what will be the resultant impact on the environment has to be calculated. For that case, we can use LCA methodology to calculate the impacts when the RCA can be used. So we have proposed a framework called ab initio framework to calculate the impacts for cement and concrete system. So we proposed this framework when there is no database was available when we started off doing life cycle assessment studies for Indian case. So this framework follows the 4 steps: goal and scope, inventory analysis, impact assessment, and interpretation, as followed by anybody else to conduct the life cycle assessment studies. The difference is only the inventory analysis and the impact assessment. So in inventory analysis, we had to collect the data which was not available. So we went to different cement, aggregate, and concrete plants in and around India to collect the data. Then when coming to impact assessment, we select suitable conversion factor for each input that we considered in the data. So this is the 2 steps that will be quite different from the other studies in the present framework. So the first step was to understand the goal and scope. Our goal was to calculate the impacts due to concrete or cement production in terms of CO2 and energy consumed. We selected different system boundaries like ground to gate, gate to gate, to understand the influence of different system boundaries on the total impacts calculated, that is CO2 and energy. So we had different functional units based on the input. It was ton of clinker and cement, and it was 1 ton of aggregates, and it was 1 meter cube of concrete, depending upon the system and depending upon the material. So we also try to understand the different technologies like dry processing, integrated cement plants, and grinding unit in case of cement. In case of aggregate, it was only crushing. In case of concrete, it was concrete batching in an RMC plant. So I would like to take the example of aggregates in order to explain the framework that we followed. So for aggregate production, we visited 1 aggregate crushing unit in Kanchipuram in Tamil Nadu, India. And we considered different process like the quarrying process, where the rock boulders are being produced and later transported to the aggregate crushing unit, where different process where the aggregate has to go through different crushing process in order to get the output material. We also considered different processes, different system boundaries like ground to gate and gate to gate. In ground to gate, all the process was considered, but in gate to gate, only the process which is happening inside the crushing unit was considered, along with the transportation of boulders to the aggregate crushing unit. So what kind of data did we collect? We collected the data such as the material used in drilling, blasting, size reduction, and everything from the quarry. Then we collected the data like amount of input materials used for the 1 ton of output, and electricity used in crushing process, diesel consumed in loading and unloading, diesel consumed in electricity generation. All these kind of data was collected from the aggregate crushing unit itself. We also spoke to the drivers in order to understand how much fuel was consumed in transporting the materials. We were dependent on the Google Maps for the transportation distance, and also we were dependent on the Ecoinment database, that is secondary data for the upstream process like machinery used, construction facilities for the aggregate crushing unit. So how did we do all this thing? With the help of questionnaire. So these were the 3rd and 4th step, that is the impact assessment and interpretation. So these are the impact assessment results that we calculated for the natural aggregates that was produced in the aggregate crushing units visited. We see that with the change in system boundary, the impacts are changing, obviously because few of the processes which are not considered in the gate-to-gate system boundary, and majority of the impacts are because of the diesel, electricity, and transportation. In terms of ground-to-gate system boundary, we saw that the upstream processes were also responsible for majority of the impacts. The same methodology, we extended it to recycled aggregate production as well. So what kind of data did we collect? We collected data such as amount of materials, what is input and output, electricity consumed in the crushing process, diesel consumed in loading and unloading the materials, diesel consumed for electricity production in case we don't get electricity from grid, water consumed, and the source of C&D waste, whether it is from demolition site or it is taken from transfer station or from the construction sites. So we are also dependent on the survey with the drivers and Google Maps and Ecoinment for the other process mentioned, and we also did the with the help of questionnaire we were able to collect the data. In terms of recycling units in India, we can collect the data from centralized recycling facilities, or we can also go to the mobile crushers. So in case of centralized recycling facilities, we visited one of the plant in Chennai. And these are the process involved there. We could see that the demolition waste is actually transferred to the transfer station, later transported to the recycling facilities. In the recycling facilities, there were several processes, like the materials will be broke down to less than 500 mm. Later, it will go through 2 stages of crushing, and later there will be screening, and the finer materials will go to VSI. So all these processes were considered. And the advantage of using the recycled aggregates is there will be avoided impacts due to landfilling, also avoided impacts due to extraction of natural materials. In case of the centralized recycling facilities, there could be marginal decrease in the cost and better dust noise control, and we need not worry about the crushing process happening next door. Secondly, we could also go to mobile crushers where the recycling can be done. This was one of the case study that we did, where the construction waste, that is the pile caps, were transported to the crushing units, mobile crushing units, to get the recycled aggregates. So the major advantages of using the mobile crusher is there will be avoided transportation, and related cost and impacts can also be reduced. And obviously there will be the other two avoided impacts due to landfilling and avoided impacts due to extraction of natural aggregates. There could also be reduction, avoidance of gate fee as seen in the centralized recycling facilities. The handling of waste could be easier in this case, and there will be lesser uncertainties in case of raw materials availability. And we also saw what is the transportation distance of the materials. For the previous case study we did for concrete, we did the transportation distances. We collected the data for concrete production. We knew where were the materials coming from. Similarly, for recycled aggregates, we saw that what are the transportation distances. These are the transfer station, and these are the 2 recycling facilities which are established in Chennai right now. This was based on the report that was submitted by IIT Madras to the Greater Chennai Corporation. We saw that the nearest transfer station for the C&D waste to the Perungudi plant was around 10 kilometers. And if in case these aggregates has to be transported to the RMC plant, that is around 20 kilometers. So with these transportation distances in hand, with the data that was collected, we were able to do the impact assessment for recycled aggregates. So this is the results of the LCA work done for the recycled aggregates. The processes considered were the transportation of C&D waste to the recycling plant, and all the processes that is happening inside the recycling plant. We saw that the impacts with respect to natural aggregates and the recycled concrete aggregates, there was a very slight difference, because the inputs, that is the diesel and electricity, were very similar in both the cases, because in both the cases it was just crushing and we did not have a lot of difference. What made a lot of difference was the transportation distance. So here the critical parameters which decides the impact was the transportation distance. And it should also be noted that we did not calculate the other impacts or the avoided impacts due to landfilling or the corresponding transportation distance, and how much of natural resources saved, which also has to be calculated, which was not done in the present framework. So we understood that the transportation distance was the critical parameter here. Hence, I did a small sensitivity analysis to understand what is the influence of the transportation distance on the total impacts. We saw that the CO2 emissions and energy both are increasing with the increase in the transportation distance, and with the 100-kilometer distance transportation of C&D waste to the recycling facilities, the impacts can increase up to 100% in case of CO2 and 125% in case of energy consumed. And we also observed that if the transportation distance of the C&D waste to the plant is kept less than 22 kilometers or 32 kilometers, the impacts will be still lesser than that of the natural aggregates. So moving on to the conclusion, the Ab Initio framework that we used to calculate the impacts were also could be easily used to calculate the impacts of RCA production. The mobile crushing units or the centralized facilities can be visited to collect the data. And the environmental impact of RCA was slightly different or very similar to that of natural aggregates in case of gate-to-gate system boundary. And transportation distance was the critical parameter here. Other advantages such as savings in non-renewable resource, avoidance in landfilling should be quantified by expanding the system boundary in the same ab initio framework. And the impacts of concrete can also be calculated using the same framework. But for sustainability assessment, when you consider the overall performance of the RCA, the properties of the RCA on the properties of the concrete, or the influence of RCA properties on the concrete properties, should also be included. Thank you, everyone. I would like to thank the collaboration of aggregate and recycling plants in order to collect the data for LCA. And I would also like to thank the research grant for TLC from IIT Madras for the present study. Thank you, everyone.
Thank you, Anusha. Now I request Dr. Shaukin Ruwan. Shaukin, are you there?
Yes. Can
Okay.
you hear me?
Hi. How are you?
Yeah, good.
So,
Long time no see.
Yeah, long time. So I'll just introduce yourself for the interest of the participants. So right now, Dr. Shaukin is an assistant professor at Zhejiang University, China. So today he'll be talking on the LC and the CO2 sequestration potential of recycled concrete. Yeah, please go ahead.
Hello, everyone. So I'm very glad to see a lot of old friends on this web seminar. And today, my topic is about the LC and carbon dioxide sequestration potential of recycled concrete. So this presentation will be divided into two parts. The first part is about the recycled concrete powders. So we try to use the CO2 sequestration to check its potential in this area. The second part is about the recycled concrete aggregates. We try to use the nanomaterials to enhance the performance of recycled concrete aggregates. And then we performed an LCA analysis, life cycle analysis in terms of the environmental impacts of the production of the recycled concrete aggregates. So first about the CO2 sequestration. So as we know, the concrete is the second most utilized material by mass. And however, so it emits a lot of carbon dioxide. And so we proposed several methods that one of them is called the carbon capture and storage. And in this study, we try to use the recycled concrete powders, that is without any aggregates, to sequestrate the carbon dioxide and capture them and store them for a long time. I'm sure you have already seen this picture in Michael's presentation. So first, that is called the raw materials acquisition, then is concrete production. Then, during this process, it emits a lot of carbon dioxide. So after the disposal of the concrete, so we separate them. So one is called the recycled aggregates. Another is called the HCP. HCP, we call this the hydrated cement powders or concrete powders. Then we try to use the CO2 to cool them, and the CO2 can be permanently stored in the hydrated cement powders. Then this CO2 can be released again after the process of calcination, and maybe finally, I think the CO2 can be reutilized. So this is just a very very naive technology made for the transportation of CO2 by the use of the hydrated concrete powders. So this is the exact process. So first, in this study, we try to investigate the role of the water in this process, in the process of the carbon dioxide sequestration. So we try to use two types of the water content. One is without any water added. The second one is we use the powder to water ratio is 0.4, and we use several analysis methods to investigate the carbonation phases formed and the carbonation degree. And this is several photos. The first photo is about the carbonated hydrated concrete powders. Then we grind them, then we calcine them again, and finally we use the CO2 and to recarbonate them again. And this is the exact group and contents and processing procedures and the processing conditions we used in this study. That is CO2 sequestration, and here are some very initial results, and we find that is a combination of the hydrated concrete powders resulted in the formation of the hydrated carbonate. That's we call this HCP carbonated, and we found there's a weight increase up to 24%. That is also the calcination of the hydrated concrete powders also led to weight reduction. Yeah, yes, as expected. And the weight reduction is around 36%. That is another picture that we show about the mass increase. And we find that is the role of the water is quite important, the 0.4. And if we add some water ratio, like we use a water ratio like 0.4, there's a massive a great mass increase. That is 30% versus the 0.5%. So this is quite different. And the recarbonation process, although all the recarbonation efficiency is quite high if we use some water during the recarbonation process. That is, we find that is a very high intensity of calcite. Yes, this is, I think this is already reported in a lot of studies. And the calcite can be observed in the hydrated concrete powders or the hydrated recarbonated powders with water added. But no pronounced variation can be found from the hydrated concrete powders, carbonated powders without any water added, and indicating that is, the importance of water that can be very important to sequestrate the CO2. That is about the FTIR curves, and we can find that is the absorption of the HCP and HCP calcium and HCP recarbonated at about 1,430 cm was weaker, much weaker than the rest samples, which means the OH or the pH is quite lower during this process. That is also the TG and HCP carbonated and HCP recarbonated 0.4 reveals a great mass loss at around 600 to 800 degrees, demonstrating a relative high CO2 sequestration. And also the TG also confirmed the role of water in the process of carbonation. That is some chemical formula that is it's quite simple. The tested the CO2 uptake ratio was quite low, is lower than the theoretical value because there are a lot of some water loss during this process due to evaporation, and then the dense layer formed on the surface of the concrete may prevent the further carbonation, and meanwhile we can find that CO2 could only be sequestrated when Portland formed. So that's why the role of water is quite important during the recarbonation process. Then the second part is about another topic that is about the LCA of the recycled concrete aggregate, recycled aggregate concrete. That is, we call this, actually we use this to make some structures, but these recycled aggregates are strengthened by the nanomaterials. And of course, there are several ways to intensify the recycled aggregate concrete, like mechanical grinding or heat grinding or water pre-soaking. But there are some advantages. So this in this study, we try to use the nanomaterials. Then the nanomaterials have been involved during the sample preparation to boost the mechanical performance and the durability. And there are some advantages. That first is about inner feeling. That is about the facilitate the early hydration of the cement samples and improve the mechanical properties of concrete. That is, it can enhance the durability of reinforced concrete structures. And I want to first introduce you a picture about the age of a structure. There's a surface life that can be divided into two parts. The first part is about the time needed for the passivation of rebars or the steel. We call this steel. And the second is the time needed for the cracking of the concrete cover. Then after you add T1 and T2, then we can call this the service life, or this can be called a two-phase model of concrete structure service life. And these are the models or the calculation process and to calculate the concrete structures surface life. And this is about the concrete structures serviced in a marine environment. This is concrete structures serviced in a natural environment. These are different. And for the marine environment, the environment is harsh, more harsh, and there are a lot of salt, chloride, or the wind. So the situation is more complicated. But for the natural environment, it's much simple. And so these two models are different when calculating the surface life of concrete structures. And to get this surface life, so we need to first know the compressive strength and the chloride diffusion coefficients. And meanwhile, we need to know the exact process of the natural concrete production, or the nano recycled concrete, and the nano materials strengthened recycled concrete production. And these are the two illustrations of the production process. And then we get some results. The first result is about the surface life, and we can find that is after we add the nanomaterials, the recycled concrete, the structure has a longer surface life than the recycled concrete without any nanomaterials intensified. And also as expected, in a natural environment, the surface is much longer. This is of course right. That is the nanomaterials, the transportation of distance, because when we use the recycled concrete, we don't need to transport the natural aggregates from a long distance. So we can cut down the transportation distance, and it's considered to be one of the contributors that save energies of the concrete production. That is, we can find that is the use of recycled concrete greatly lead to a much lower score of damage to human health and ecosystem quality. And also the use of nano materials can only brought about a limited increase in the score of damage to resources, while the rest two damage category did not change too much. Then we can also find that in terms of the energy consumption, we can also find compared with that of the natural concrete, a reduced rate can be found regarding the energy consumption. This is due to the cut down of the transportation distance, also the elimination of the raw materials acquisition. So the energy consumption can be greatly reduced after we use the recycled concrete. But there's a slight increase about the energy when it's associated with the production of nanomaterials can be seen from the figure. That is also, we can find that is in terms of the carbon dioxide emission, I think this is quite important. And the recycled concrete can lead to 14%, about 40% reduction in CO2 emission than that of the natural concrete. And also the use of nanomaterials, I think sometimes can also result in an additional emission of the 47 kilograms of carbon dioxide, revealing that the treatment of the recycled aggregates will not, with nanomaterials will not greatly aggravate the climate change resulted from the recycled concrete production. That is the concrete strength. We also consider the strength. So in this part, we combine the concrete strength and the environmental impacts. We consider these two parts at the same time, and we can find that is if we add some nanomaterials, the carbon dioxide intensity is greatly reduced compared with the natural concrete and the recycled concrete. Then the same scenario goes to the energy intensity. But in terms of the single score intensity, the benefits of nanomaterials and nanomaterials addition is not very much. You can see from the second column and the third column, that is the RC and the nanosilicate and intensified RC. They are quite similar, the single score. The single score means the overall environmental impacts. That is concrete surface life, that in a natural environment, that we consider the environmental impacts and the surface life at the same time. And we can find that is, actually, when we consider the surface life, as the recycled concrete has a shorter surface life. So when we combine these two factors into account, so the recycled concrete, the CO2 intensity is the highest compared with the two groups. And also the same scenario goes to the energy intensity. But as we can see from the overall environmental impact, that is the single score intensity, the figure C here, that is, we can find that nanomaterials is beneficial in terms of the single score intensity. That is the concrete surface life in marine environment, and we consider the surface life in a marine environment and the environmental impacts at the same time. And the situation are quite different. And we can find that is the recycled concrete, without any nanomaterials in treatment, has the lowest the carbon dioxide intensity. And also in terms of the, sorry, there's a mistake here. Also in terms of the energy consumption, the RC and the nanomaterials intensified RC are also quite lower than the natural concrete in terms of the energy intensity. And finally, in terms of the single score intensity, and the RC and the nanomaterial intensified RC are also quite lower compared with the natural concrete. Then, as we know, there are a lot of data. These data are from different sources, and so the results can be varied greatly sometimes. So here we conducted some analysis called the Monte Carlo analysis. That is we also call this uncertainty analysis, and we can find through a lot of rounds, like 1,000. We finally get distribution, the probability distributions curves here. And the first curve is about the CO2 emission. And we can find that is the proportion of nano-silicate intensive RC emitted less CO2 than the RC and the natural concrete. Then we can also find that it also has a lower energy consumption and a lower single score. So here, the final part is about the conclusions. And we can find that is the nanomaterials can enhance the service life of structures with recycled aggregates, as well as its sustainability. And then the recycled concrete powders shows the great potential in CO2 sequestration. So this work is funded by the UKIER. EST is a project which is called a new framework of high value added zero waste recycling of concrete from construction and demolition waste. And the aforementioned research work has been published in 2 journals. One is called the Journal of CO2 Utilization. Another is called the Journal of Greenhouse Gases, Science and Technology. Okay, thanks.
Thank you, Shokin. So now we have finished our session 2. Now we'll be starting with the session 3. So for the session 3, we have Dr. Boksun Kim, who is an associate professor at University of Plymouth, UK, and today she'll be giving a talk on recycled aggregate concrete, the scenario in Southeast Asia. So I request Dr. Kim. Yeah, she already shared her screen. Kim, you can, yeah, I think you have to unmute yourself also. Can you hear me?
I can hear you. Right.
Yes. Okay. That's fine.
Yeah, you can see my screen.
Yes, I can see. I can.
Yes. Good morning or good afternoon in India. I'm Boksun Kim from Plymouth University, and I'm going to talk about my research in recycled aggregates in concrete construction at the University of Plymouth. I've got 3 funded projects at the moment, and I'm going to talk about one by one. And then I'm going to show you a couple of case studies, followed by upcoming events. Briefly, I do research on cementitious materials with recycled aggregate, with graphene oxide, and also with plastics. With this graphene oxide, the concrete with graphene oxide flakes, there will be a PhD studentship advertised next month. So please keep an eye on our university website if you are interested in. And I also do research on cold form sections, especially with holes on the web. and one of my PhD students has just completed his study on this. I've got 3 funded projects at the moment. And the first one is funded by EU. It's called Tailor-Made Recycled Aggregate Concrete, TRAC for short, TRAC. This is a website for this project. It's a 4-year project, started 2018, but due to pandemic, we couldn't travel. So we got extension until next year. This is a RISE project, RISE. So that's research innovation staff exchanges. So we go to outside the UK, so overseas universities, and then overseas researchers come to EU. So in there, we collaborate in research. There are 5 partners in this project. UOP, my university is a coordinator, led by my colleague, Dr. Shanshan Chung. And we have a European partner at Chalmers University of Technology, Professor Luping Tang. And we have 3 overseas partners, PNRU in Thailand, and TDTU in Vietnam, and Shenzhen University in China. So we have several work packages. At Primus, we look after the research in fire performance. And we also do some durability tests like chloride migration test. Last year, I was very fortunate to be one of the 13 Frontiers Champions funded by Royal Academy of Engineering. So it's supposed to be a 1-year project, but due to pandemic, I had a 3-month extension, and this one is about to finish next week. So it's nearly finished. And as a Frontiers Champion, and I established a consortium for recycled aggregate in concrete. And I'm going to show you this. So this one, and I show you this. So this is our consortium in LinkedIn. So this is open for global research communities. So if you have not joined, then please join us. And we welcome policymakers, practitioners, as well as engineers and researchers and social scientists. The more the merrier. So currently we have 153 members, and we use this LinkedIn group as a vehicle to advertise the event. You can see that the one you are doing at the moment, we are doing at the moment, and also we disseminate research outcomes. So as a Frontiers Champion, I hosted 10 webinars last year, and 1 online and 1 in-person workshop on the development of recycled aggregate concrete. And the webinars are recorded, and the recordings are available on the project website along with presentation files. And I'm going to show you the website briefly. Yes, this is the project website. You can see, you can read about myself as a Frontiers Champion. And then we have a video clip here, made by the Royal Academy of Engineering. And I'm going to show you this later on briefly. And under event, you can see the presentation files and also recordings of each webinars. Thanks to the speaker's permission. And this place is really good for somebody who wants to learn about recycled aggregate. And so for your PhD students or undergraduate students or MSc students. Right. Okay. So these are the 10 webinars I hosted last year. So you can see from basics to design and properties and strengths and so on. So you can find very famous people here, world experts. I'd like to thank them to donating their valuable time to the webinar. So some stats, about 1,000 people registered. However, about half attended from 42 countries. Of course, the majority they came from UK. Sorry. So the majority came from UK, followed by India. Yep, India. So huge interest in India and Ireland and Malaysia and Singapore. So this figure gave us a really, really good insight. So advertisement was very important because not everybody attends. It's easy to register, but not all will attend. So that gave us a really good insight. So in the future, we'd like to have more advertisement. If I do this project again, I would spend some money to advertise this workshop. And at registration, about a quarter of the delegates were female, and then about half, just over half, were from industry, so practicing engineers, and a quarter was about academics, and then 1/3 were students, including PhD students. And at registration, we asked delegates what question they would ask the speakers. So there was at registration prior to webinars. The most popular one was about properties. The blue one here, properties, such as strength, stiffness, durability, and general performance, and followed by production, mixed design, and policies. So these questions were sent to the speakers before their webinar, so they can include this into their presentation. Last July, I hosted an online workshop, and we talked about case studies, and I'm going to present 2 of them here. This one is from Vietnam by Mr. Quinn, who is the director of Lego Tang Cow JSC. Vietnam loses 5%, about 5% of GDP each year due to the non-efficient waste management. Vietnam is a developing country, as you know, and very active in construction. That means thousands of tons of construction and demolition waste are produced every day. So the most CND waste is used leveling riverbanks, shown on the top left, now this one. So without any processing, they just move and they just pile them. That's one of the easy way they can do. And currently, recycled materials are about 30% cheaper than rubber sand for leveling. And one of the key issues they have is lack of space to store recycled materials. Yes, there are some regulations exist, and however, recycled aggregate is not allowed for structural purposes. On the bottom, the two photos here, these are examples for applications. So the concrete paving blocks, using recycled aggregate, and then this one is for unburnt bricks. So Vietnamese government recommends to produce unburnt green bricks. As you know, conventional method, you have to burn this, and burning requires energy and hence high CO2 emissions. And this study was presented by Mr. Narom Wongasem of CPAC Construction Solution in Thailand. His company does a lot of work on this recycled aggregate and trying to have circular economy solution. On the top left, you'll see the three construction phases. The blue one, earthwork, and then concrete. Red one is concrete, masonry, and mortar, and then green one is the others. What they do, they have design team and working with their clients, and then trying to provide a tailor-made solutions. And the company is trying to do a zero waste one side. So it's better if you don't have to move the C&D waste to the recycling plant, if you can do on site. But that's really challenging. And the last one is, despite Omicron, I had a window of opportunity to fly to Bangkok last December to host an in-person workshop in Bangkok. That was absolutely fabulous, and to see everybody in person. And of course, some delegates could not attend because of Omicron, especially from Vietnam and Malaysia. And during the workshop, we discussed lots of things, and some current updates in recycled aggregate, and also we had the breakout sessions in the afternoon. And 3 themes we discussed. The first one was the barriers. What is the barrier to in the development of recycled aggregate concrete in Thailand? And they said that government policy, lack of government policy, and followed by cost and research knowledge, and then social acceptance, especially public awareness. And the challenges, technology methods, that was the biggest one. Yep, we need a good technology, and followed by eco-friendliness, as all know that climate emergency, and they want to produce less carbon concrete. And hence opportunities lie technology side, and followed by eco-friendliness, and the industry and companies who need to collaborate with them. Hence the challenges and opportunities. Developing countries produce a large quantity of construction and demolition waste, and currently there are lack of recycling plants and facilities. Yes, to have large recycling plant with equipment and infrastructure, it needs a lot of investment. And the location of the recycling aggregate plant was also important. Huge demolition, a lot of demolition, and the new building happens on site. However, the recycled aggregate plants are outside, away from cities. So transportation cost extra, add extra cost. And currently, cost is a barrier. Yes, we found that no policy or little policy or standardization for the use of recycled aggregate, especially for structural purposes. And quality control and classification is the key. And the design guidance and design strategy needs to be developed further. Currently, many countries use just the foreign standards, for example, ACI. And we thought that design for target strength is a good approach. So, for example, you can target like C30 or C40, and then from that point, you can go back and then develop target strength. One of our outcomes out of this Frontiers Champion project, I have been invited to a task group, one of the task group of International Federation of Concrete, TG 4.7, that's structural application for recycled aggregate concrete. And we are working on bulletin, and I am about to contribute one section on chloride ingress in recycled aggregate concrete. And the Royal Academy of Engineering has made the series of net zero videos. And the second one is about built environment. And so hope it works. And I appear, yeah, it's a just over 30 minutes, but I'm not going to turn all the way. I appear about 10 minutes. So here.
Dr. Kim, I think the audio is not there. We can't hear, but we can see the video.
Yes, yes. With me also same.
Maybe you can share the link, maybe so we can watch it later in the chat box.
Perhaps send a message. It seems that she can't hear us either.
Okay.
I need to stop this.
Yeah, Dr. Kim, we were saying that
Oh,
we can't hear the
my-
audio.
My cursor is stopped. I need to stop this. So unfortunately, my cursor is stopped. So I can't stop it, this one. So I may need to log out and log on again.
Yeah, sure, please.
Sorry about this.
No problem.
No problem. No problem.
Somehow, sorry. Sorry, somehow I can't stop this one. My cursor is there, and I still log
Maybe
out and log on.
you can try the option of escape from your keyboard if you want.
My cursor is stopped.
Okay.
So maybe we will try removing you and then you can log in later. I think now we can see some other screen maybe.
Yes, yes.
Dr. Kim, can you hear me? I think there is some problem. So we will just remove her and I'll send her a message that she can join again.
Yes, yes. Please do it. Yeah, in between, I request the participants to, if you have any questions, you start posting it in the chat box, right? The participants who are watching through YouTube, they can put their questions in the chat box there itself, and then our moderators will be picking the questions from there and then posting it here. Okay, so you can start posting your questions now until Dr. Kim joins. Rohit, in between, you can send her one email also.
Yes, sir.
Share-
We'll try contacting her, sir.
Yeah. And share the Zoom link again with her. Okay. Yeah, I think in between Dr. Yunus also mentioned that he could chat with her. So Dr. Yunus, if you have
Sir,
her
I
contact-
think she's not able to join back, and we're running out of time. So maybe can we proceed with your talk?
Yeah, maybe we can wait for 10 more seconds. Did she reply?
No, sir. I think we cannot see her request on Zoom also again. So I think there's some
Okay.
problem with the computer, maybe.
Oh, okay. Yeah. No, in between, Dr. Yunus also mentioned that, he sent her one message. So, Dr. Yunus, if you have her
No, I
contact
suggested
details-
that I suggested that we
Okay,
type a
okay.
message in the chat, but it didn't. She'd left by then. Yeah. Anyway,
Okay.
I agree. I think perhaps we should just go ahead. Yeah. Thank you.
Yeah, thank you, Dr. Yunus. Thank you. Yeah. So anyway, we are already running out of the time. So, when Dr. Kim joins, we'll ask her to again share her screen and then finish her presentation. But in between, so I'll start presenting my screen. I'll take you to the state of the art on C&D waste recycling in India and what are the projects that currently we are doing here at IIT Madras. Okay, so I'll just share my screen. Okay, I hope you can see my screen.
Yes, sir.
Okay, can you see my full screen, Rohit?
Yes, sir.
Okay. Again, a very good evening, good morning, and good afternoon to everyone. So I'm Surinder Singh. I'm an assistant professor in the Department of Civil Engineering at IIT Madras. And today, on behalf of our team members who are working on the various aspects of the C&D waste, I'll be presenting the work that currently we are carrying out as a part of our Center of Excellence on Technologies for Low Carbon and Lean Construction, which Professor Gettu has already discussed briefly. So we recently received one prospective Center of Excellence, wherein we'll be working on different aspects of the C&D waste. So you can see these two pictures here. One is, the recycling is happening at the plant. And nowadays we are also going with the on-site recycling processes also. Okay, so both the pictures I have taken from Chennai itself. So as we mentioned, our prospective Center of Excellence, the main mission is to develop India's first integral test bed for evaluating the uses of agricultural, industrial, and C&D waste in concrete for directing practices, policies, and standards for waste reduction in construction industry. So our intention is that whatsoever the waste that is coming, whether it's the industrial waste, whether it's the agriculture waste and the C&D waste, we should be able to develop strategies and the techniques to produce high quality material, right? So currently we are exploring on various agricultural waste such as rice ash, bagasse ash, right? Other industrial waste also, and then obviously on the C&D waste. Also, we are looking into how to reduce the process waste that is happening. In fact, you'll be amazed to see that the waste could take place before the construction even starts. So that is also there. And the approach that we are following is from problems. We'll be looking into the problem statement, and then doing the research, both the fundamental research as well as the applied research. And through this systems thinking, will be formulating the policies that could be applied in the field. So it's not only the laboratory, but will be going into the field. So this is our COE team. And you can see here we have a wide range of experts working on different aspects such as construction materials, construction management, and building science. So today I'll be focusing my talk only on the C&D waste. I'll not be touching the agricultural waste and the other waste. So as far as the scenario in India is concerned, we see that India is already very near to China in terms of C&D waste generation, but we don't have that much of we are not able to map the exact quantity of the waste. So different reports are there. They are suggesting different amounts of the C&D waste that is generated in India, right? And then we have seen that lot of dumping activities are happening. Because of that, we are not able to map it. But anyway, in 2016, the maximum projection of the C&D waste that has been estimated is around 716 million tons, right? So when we goes into the field, like Professor Kim was also mentioning, why we are not able to use the C&D waste. And one of the other attributions is that the hesitations amongst the field engineers, and then also people also think, why to use the C&D waste when we have a good supply of natural aggregate. So we did the analysis. What we found that per annum in India, we need around 751 million tons of sand. And in most parts of the country, the sand is already banned. Okay. So now we are looking into the possibility of using the crushed stone, okay, sand. That means while we are crushing these stones, this dust that is generating, we have started exploring the use of that for concrete application. So if I talk about I think somebody has to mute himself or herself. Rohit, can you mute yourself? I think you are. Or Paresh Parmar, can you please mute Paresh? Okay.
Yeah.
So, okay, thank you. So, in case of the crushed stone, if you see, we per annum requirement is around 1.6 billion tons, and we have ample supply, 126 billion tons, right? If let's say if you started using the crushed sand also, then also the per annum requirement is around 2.2, 2.3 billion tons. And but most of these resources are in the reserved area where we cannot do the mining. And if I talk about the limestone, it is expected that if the rate of consumption and the rate of production to be same, keeping the same, in next 40 to 80 years, will be exhausting the entire amount of the limestone that is available for mining. So that's why now in India also we have started paying attention on recycling, C&D waste recycling, and we have come out in India right now. We have around 12 recycling plants, 3 in New Delhi, that is our capital, and as far as right now we are in Chennai. So we helped the Greater Chennai Corporation to establish 2 recycling facilities in Chennai alone, right? And then with the quantum of the waste that is generated and with the 12 recycling facility, we are not able to, in fact, recycle around 2.5% of the total waste generation. That means we need more recycling plants. So the ministry has mandated that every city having a population of 1 million need to have at least 1 recycling plant. So in the next 10 years, we might be able to see more than 300 plants all across the India. Okay, so that means there is a huge possibility now. So what we did, we went to different recycling plants. We collected the data to see what is the range. Is there any difference in the quality of the recycled concrete aggregate? So we did it in Chennai for multiple plants, but here I'm showing only the average value, Delhi, in Roorkee, and in Bangalore. So what we found that the specific gravity is more or less is same. Water absorption, this is only coastal fraction. So finer fraction, the specific gravity is was around 2.1, and the absorption, if I talk about it was also near to be 5 to 6%, and for the fine aggregate it was 8 to 12%. That means it is significantly higher. Okay, these are the other physical properties that are required. So in India right now we have the codal provisions. Okay, 2016 we had codal provisions to use recycled concrete aggregates, right? Like Rohit has already mentioned, 25%, 20%, or 100% for lean concrete. So whatever the aggregates that we have guided from different plants, it seems to be satisfying the norms, right? At least for the non-wearing courses. Like if I talk about the payments, base layers, not for the wearing courses, right? It's not only the specific gravity and water absorption, but also we need to characterize the other physical parameters. So if we compare our guidelines with the guidelines or the provisions available followed for different countries, we see that the different countries, some of the countries are too stringent. They ask for 2% of the water absorption, but we know the water absorption of the recycled concrete aggregates is significantly higher. Why is it so? It is because of the added mortar content. So this is the natural aggregate. Recycled concrete aggregate is also a natural aggregate, but it will be surrounded, or at different patches, you will be seeing added mortar from the old parent concrete, which is highly water absorbent in nature, right? So how this will be affecting your concrete? Like Rohit has already mentioned that, in case of the normal concrete, there is only one interfacial transition zone. And when you apply the loading or any loading is coming, interfacial transition zone being the weakest link, the crack will propagate through it. But in case of the recycled aggregate concrete, when you are using recycled concrete aggregates in the concrete, then there could be different failure pattern. Mostly the mode 3 and mode 4. That means the weak zones in case of the concrete, in case of the recycled aggregate concrete, will be either the adhered mortar or interfacial transition zone between the old mortar and the aggregate. But we are the engineers, so what we have to do, we have to engineer this material in a certain aspect, like Dr. King has mentioned, tailor-made recycled concrete aggregates, such that we can control this failure pattern. Control means the crack should propagate through the new mortar, so we can control it, right? We can control the properties of new mortar. And interestingly, can we make our concrete, recycled concrete aggregates so strong that it is stronger than the aggregates? Can we do it? Yes, we have to look for this scenario. But so right now, our current work is to shift the failure mode from mode 3 to mode 4 to either to mode 2 or mode 1. If I talk about the special kind of the concrete, let's say pavements or roller compacted concrete, apart from the interfacial transition zone, the load carrying capacity of those mixes also depends upon the aggregate to aggregate interlocking. So let's say if you are using the recycled concrete aggregate and has the added mortar content, so the aggregate to aggregate interlocking capacity will be affected, right? So we are also exploring on how to enhance, like Rohit has mentioned, how to remove the added mortar, right? But if you want to use it in as received state, then we need to enhance the bonding between the old mortar and the aggregate, or we need to address the issues with the old mortar. So right now we are also working on strengthening the added mortar so as to have better interlocking capacity and thus better load carrying capacity of the mixes. So we thought, okay, we'll be starting with the base, right? So normally what is happening, all across the globe, normally when a building or any other concrete infrastructure, it is demolished, so manual sorting will be happening. Most of the time, plastic and steel will be sorted during the demolition stage only because they are having high residual value. Then they will be brought to the recycling plant, wherein in the recycling plant, because some of the soil fractions will also be there, excavated soil, so we can just put it and then we can vibrate it so that we can remove the soil from the recycled concrete chunks. And then mostly we are just, with the help of the jaw crusher, we are just resizing the aggregates into coarse aggregate and the fine aggregates. And what we have seen in India, now we have two-stage crushing, right? So one jaw crusher after the other jaw crusher, so that the size reduction could be significant, right? And then we can see that apart from the coarse aggregate and fine aggregate, we can also get the concrete fines. Now, right now we are exploring how to use these recycled concrete fines, because maybe it can be used for cement regeneration, right? It can be used for the carbon sequestration, as Dr. Sean mentioned, right? And nowadays, the most advanced facility is also keeping one more crusher, that is vertical shaft impact crusher, for enhancing the morphological properties of fine aggregates. So like VSI, that is vertical shaft impact crusher. And then if we talk about the on-site recycling, so on-site recycling could be a stand-alone unit of VSI or the horizontal shaft impact crusher. Okay. So right now what we are working, we are optimizing the crushing technique. We are understanding the crushing technique and optimizing it, not only based upon the cost, but based on the energy consumption, how much CO2 emission will be there, right? And then the aggregate properties, especially the morphological properties, because if you go, in the jaw crusher, you apply the compressive stresses, in the impact, you apply the impact. So there could be changes in the morphological properties of the aggregates, and then it can have the effect on the aggregate to aggregate interlocking, and also how much it will be affecting the other mortar. So all these parameters will be affecting the strength of the concrete. So we are working on this. The second thing is that, let's say after you were getting the aggregates from crushing, so we are focusing on addressing the existing issue with the adhered mortar. So you might be knowing that the issues with the adhered mortar is it is highly porous. You might see some cracks, right? You might see some cracks in the existing mortar, and then the interfacial transition zone between the aggregate and old mortar will be very, very poor. So what we are doing, we have different techniques available to do it, right? So one of the most important technique and highly promisable that you can use it for the large scale applicability in the field is a slurry impregnation technique, wherein different cementitious materials are mixed with the water, and then the recycled concrete aggregates are soaked in it for different durations, right? And after that, we take it out and dry it, and then we can use it. So, but this slurry impregnation technique, it's an initial work. So we are right now optimizing it because the porosity of this adhered mortar is a function of many things. First thing, from which source we are getting the aggregates, right? What is the size that we are considering? The porosity is also a function of slurry material, because let's say if you have a microsilica and a fly ash, both will be having different fineness. Both will be having, if I compare with the GGBS, so both will be having different composition. Okay. And then similarly, how much of this slurry concentration should be there? For how long should we keep the aggregates in the concentrated solution, right? And also for how, whether you are able to mix the slurry effectively or not. So all these things will be affecting the porosity of the recycled concrete aggregate and thus the quality of the aggregate. So currently we are working on it. Also, we are planning to use this technique to improve the properties of recycled concrete aggregates so as to use for ultra high performance concrete, wherein the strength requirement is more than 80 MPa. So we are exploring these options also. As I mentioned, for the pavement application or the special concrete application, the aggregate to aggregate interlocking plays a vital role, right? So in that case, what happens, normally we have the, like say 1 meter groove of concrete. We generally, most of the time, we place the aggregates. We use the well-graded aggregate, so that when you are able to reduce the porosity with the help of the well-graded aggregates, the amount of the cement that is required to fill these voids will be reduced. And then we know the cement being the most costliest component. And that's how we can also improve the interlocking capacity of the mixes, right? So right now what we are doing, we are optimizing the size of the different RCS aggregates with the help of the particle packing approach. Okay, we have different particle packing approaches. We are studying it, which is more practical to be used for increasing the densification of the recycled concrete aggregates. Okay, especially for the roller compacted concrete mixes. Then, as Rohit already mentioned, that we are working from crushing mechanism to strengthening the adhered mortar to removal of the adhered mortar, right? So normally what happens, if we know the physics and chemistry of the adhered mortar, like it has different hydrated compounds. So if you heat it for certain duration, let's say at around 450 degrees centigrade to 500 for around 1 hour, the dehydration could be happening, right? So, but yeah, for that you need a lot of energy. You need to keep it in the oven, microwave, or furnace, which is again energy intrusive, right? So what we are doing, we are exploring the options of using the concentrated solar energy, followed by, so you heat it up and then you remove it, cool it for 24 hours. So there will be some thermal shock also. And then this mortar become very, very weak. And just you have to remove this weakened mortar with the help of the, you can create some mechanical stresses over it with the help of the bill mods, right? And you can see Rohit has also shown this figure, like in these aggregates, you can see a lot of adhered mortar, but in case of the aggregates, 20 mm, about 20 mm, you can see we could able to remove the entire, mostly all the adhered mortar content, and the quality of the aggregates were at par with the pristine aggregates. Also, we are working on the reclaimed asphalt pavement aggregate. Reclaimed asphalt pavement means when an existing asphalt pavement, or in India we're calling it a flexible pavement, normally after 1 year or 2 years of the construction, it will start showing the distresses, especially in the areas where we have a good rainfall. So when you remove this material, so here it's again a aggregate similar to recycled concrete aggregate. It also consists of the pristine aggregate, but totally surrounded by asphalt film. So asphalt film could be around 6 to 10 micrometer film, right? So the issues with this, apart from the asphalt content, which is organic in nature, so we can have the agglomerated particles, because asphalt is a glue which will bind the aggregates together, and the binding capacity between these aggregates is very, very low. So when you use it in concrete, obviously the bonding affinity of the organic coating and the inorganic cement mortar paste is very, very less. And when we have the large amount of the agglomerated particle, it further reduces the mechanical properties. So we are studying the interaction mechanism, that what are the various parameters of the asphalt coating, aggregates, or the agglomerated particle that will be affecting the bonding potential, and how to improve it. Also, we are looking into the techniques to remove this adhered mortar. Okay, because yeah, we can use benzene, kerosene, many things, but those solutions will not be a sustainable approach, right? So for that, we have to innovate something. Already we innovated one technique wherein we worked with the chemistry of the asphalt and could able to remove at least some of the asphalt. Then also for the payment applications, it's not about the stresses, tensile stresses because of the loading. The tensile stresses can occur because of the temperature differential and because of the moisture difference, right? So we are studying how this use of this wrap material will be affecting the performance of the concrete. Okay, so we are doing it. And then because in China, if you're talking about India also, we have a lot of coconuts. Okay, India is a hub for coconuts. So normally after sipping your these coconuts, we'll be dumping it, right? So lot of coconuts we can see in Chennai. So we thought, why not to use this coconut for different payment application? Can we use it? It's a natural material, right? Normally it is used for geotextile application and the other things. So what we did, we tried to remove the fibers from this coconut, and then what we found, a lot of impurities. First thing, it is very, very hygroscopic in nature. It has a lot of impurities. So we are working on developing strategies to improve the properties of this core fiber, improving the tensile strength and the durability parameters. Okay, so now you might be thinking that this square is a biodegradable, right? But for the pavement application, because pavement has a large surface area, exposed surface area, plastic shrinkage cracks are very, very crucial, right? It always happens. So can these fibers in a small amount also, if they're able to address the plastic shrinkage cracks, then it will also be very, very good. Also, but if you are using these materials and a biodegradable material, it may affect the performance of the concrete. So we're also evaluating the performance of this concrete containing the coir fiber, okay, coir fiber, so as to improve its potential. So with this, this is my last slide. As I mentioned, we have the Prospective Center of Excellence on Technologies for Low Carbon and Lean Construction, wherein we are working on different aspects of the recycling and lean construction practices. So if you are interested in collaborating with us, we are, you are, surely welcome. You can send us one email on this ID, and then we have positions also available. And then here itself, we'll be posting what are the various events or the webinars we are, conducting. So you can get in touch with us if, and obviously you can anytime message me if you need more information or if you have any issues with the recycled concrete aggregate or any kind of the waste material. So with this, I'll say thank you. And now I think we are already finished our session 3, that is on special topics on C&D waste recycling. If Dr. Kim is here, she can, we have 3 more minutes. She can, if she wants to finish her presentation, she can do it.
So
Dr.
she could
Kim,
not join.
okay,
so he has
okay.
sent the presentation, and we have asked her to send the video link so we can share it in Zoom and YouTube chat.
Sure.
Yeah.
We can do it. Okay, we can. I request you to share the video link with all the participants. Okay. Now I request all the participants, like who are on the Zoom, so they can raise their hand, and Professor Piyush Chansoli, who is an assistant professor in the Department of Civil Engineering at IIT Madras, will be moderating this session. And if you have any questions apart from the C&D waste, Professor Piyush Chansoli works extensively on valorization of agricultural and industrial waste. Right. So if you have any questions related to that, you can surely ask with Professor Piyush Chansoli. Piyush Chansoli, over to you now.
Thank you, Surinder. Thanks everyone for your participation. We have come to the last session now, where we'll take a few questions. Feel free to use the chat box to type your questions based on the lectures we had so far. So you can see that we had lectures on material processing, what are the challenges. So also how to assess the sustainability of materials and processes. So Anusha mentioned about the life cycle assessment framework, and also policy is very important as far as scaling up the use of C&D waste is concerned. So apart from material research, policy research also plays a big role. So hopefully we got a glimpse of different types of research which is being done worldwide. And hopefully this workshop will also lead to more and more participation in future, because this is a very crucial topic and we need more people who are actively involved in this research area. I guess there's one question on YouTube which I picked up, maybe Rohit can answer. One person is asking about the strength of recycled aggregate concrete, and probably it's a current application. So Rohit, can you take this question?
Yes, sir. It's from YouTube. So I think he's
Yeah.
asking for the strength. So maybe I think they're asking for the mechanical strength. So
Yeah. So how does it compare with normal concrete? What are the challenges? And also you can talk about the applications. Where can we use it? Based on your research and based on available knowledge. What are the challenges ahead? So broadly, you can answer this question.
yeah. So as I have shown in my slides also, so recycle aggregate will have this attached mortar, which is porous and weak. So all the mechanical strength, maybe impact, crushing, or abrasion value, that will be lower. The impact value will be higher. Means it can take less mechanical loads. So that adhered mortar will tend to break. So all abrasion value, impact value, and all this mechanical strength will be lower. But to start, maybe the application wise, maybe like codes also allow up to 100% of replacement for lean concrete applications. And even for the structural gate application, it is 20% of the replacement is allowed. So, and the maximum grade up to which we can go right now is allowed to M25 or M20. But if you have beneficated them, and I have showed the results, you can actually go the grade of concrete we have tried is M40. So if you have beneficated and if you're using a lot of SCMs, and practically you can get any strength you want. So, and there are a lot of codes which will not limit the extent of utilization. So up to M30, M40 concrete, you can even allowed to use recycle aggregates. But for now to start, I think there will be pavements and other maybe non-structural application would be a safe start.
Okay, thanks, Rohit. Also, those who are present here, you can unmute yourself and ask question anytime. In the meantime, Ram is available. I have a question for Ram. Ram, you mentioned about qualitative comparative assessment, and let's say someone is doing quantitative analysis. So, will your conclusions be still valid, or what are the uncertainties?
Yeah. So, of course, my conclusions will still remain depending on how we can have to apply it. For example, if you're going to take those, these are going to be useful starting points for countries like India or other places where they want to start it. And that's the first part of the answer, where it will still be valid as a starting point. Of course, I have also talked about there are multiple causal pathways that we can take, and multiple combinations also can lead you to successful establishment. And on the other hand, if somebody wants to do quantitative analysis, and of course that I have explained, will still be able to do it if they are able to manage a large data set in terms of studying. And one of the biggest drawback in terms of using quantitative methods for policy analysis is we will not be able to separate the causal pathways into coming up with the same conclusion. For example, it is predominantly oriented towards how, let's say, in a regression analysis, a particular success and particular parameters will lead to this. So that's how they will be able to analyze. However, when we are talking about qualitative studies, here we are talking about how different combinations can still lead you to a same outcome. So that kind of segregation will be a little tricky when you're using quantitative methods.
Okay.
I'm sure I've made it.
Yeah,
clear.
I think. Thanks, Ram. I think Mr. Paresh is there. Maybe you can unmute yourself and ask your question directly, Mr. Paresh.
Yeah, I just wanted to have an understanding about experience with use of what we call recycled concrete, fresh concrete aggregates, about performance and ability to recycle everything, whatever is present from the fresh concrete.
Sorry, I could not understand you. You want to ask what will be the behavior of concrete, fresh concrete, right?
I'm talking about the possibility of recycling concrete in a fresh state and reclaiming the aggregates, because we have been able to succeed in achieving what you call coarse aggregate, finer part of the coarse, finer, but not able to recycle or reclaim the finer fines. So, has anybody had an experience in recycling those and reusing it?
Yeah, so our team, I think Anusha was there. So they went to one of the recycling plants there. So we are calling it as a construction waste. So when we have the leftover material in the RMC or anywhere, like, they'll be bringing it back, they'll be washing it. And then we have seen we can able to extract the natural aggregates again from that. So with my experience, I can say the coarser aggregates can be directly used. Yeah, you are absolutely right with the fine aggregates. Like, so there, I think they were using the sedimentation process for extracting the fine aggregates. Okay, so but we need to see how it will be affecting whether the gradation will be changed or not. Okay, we didn't work on the finer fraction, but we have seen the coarser fraction quality was at par with it was in fact the natural aggregate only. So if Anusha, if you want to add in something because you were physically present during the site visit, you can do it.
No, sir, I think you've covered all the points. Yes, it is possible to retrieve all the materials from the fresh concrete and it can be used. But we did not check the quality of the materials, but it should be in par with whatever has gone into the concrete.
But what happened to in what we call a test environment? I do agree with everybody that we can recycle and reclaim 100% whatever is the waste generated. But we do have practical challenges because from this part of the world, we don't have fine sands or crushed sand. We use dune sand, which is naturally occurring. Basically, we are not able to reclaim those things because of the practical challenges achieved, and sedimentation also might not give you a practical solution to use it in live environment on daily basis.
Yes.
Yeah. So in that plant, what we visited, they were reclaiming the fine materials and they were putting back into along with the fine aggregates, that is natural aggregates, and they were using it for concrete production itself. So it takes time. It is not, you can't do it then and there as you do for coarse aggregates, but it could be done with some point of time after drying, it will be reclaimed and reused in place of natural aggregates.
Okay, thank you, Anusha.
Yeah, thank you. I think there is one question here. Basically, when we use these nanomaterials, a few speakers gave presentation. I'm not sure if anyone is here. The question is about, usually we see improvement on ITZ quality, and that may reflect in elastic modulus value. So the question is, in those studies, have they looked into the effect of the use of nanomaterials on elastic modulus of these concretes? I guess Saukin, I don't see here.
Shaukin, yes, but yeah, Penkun, Dr. Penkun, who? I'll see.
Or Michael is here, I think. Michael, can you hear me? I think I see you here.
Yeah, I can hear you. Yes.
Yeah. Just a question, because we are not able to track Saukin. That question is, when we use nanomaterials, let's say in recycled concrete, and we'll see improvement on ITZ. How does that impact elastic modulus? Has this been studied in your research group? Or?
I don't think so. I couldn't answer the question. I assume actually it probably can improve the elastic modulus, increase the elastic modulus, but I'm not quite, haven't got the data available. Okay.
Fine.
Chair, if I could just expand on the question.
Yeah.
The effect is that elastic modulus in fact increases a lot more rapidly, especially after 6 months, than even strength does. And my question relates to the possibility that these these very fine materials could help to refine at least one of the ITZs that Rohit mentions. And others have mentioned about these multiple ITZs when you are using recycled aggregates. And so it'd be interesting to see how these very fine materials affect the performance of multiple ITZ materials. Yeah, that was really based on my question. I'm just thinking about future research projects.
Yeah,
Thank you.
No, that's a very good question.
Yeah.
Again, those of you who would like to ask question, please unmute yourself, and we have some time. We have still 10 minutes, so we can take a few more questions.
Mr.
Piyush,
Sudarshan.
there is a hand raised from
Yeah,
Sudarshan.
so please go ahead. Please unmute yourself, Mr. Sudarshan. Yeah.
Okay, good evening. My name is Sudarshan and I'm actually coming from Monash University, Malaysia. I have this question regarding the handling of nanomaterials. It can be nanosilica, even carbon nanotubes and others, especially when some of these materials can be hazardous. And yeah, during construction is okay, but what happens when we wash off the mixers and then we actually let the water flow into normal drainage, and then once if they are actually dried off and then the materials become airborne, that is one concern. And secondly, can these structures constructed with these nanomaterials, can they be caught when you do the coring? Will the nanomaterials actually become airborne, and which can be a hazardous, it can provide hazardous impact to the workers which are actually there, as well as the occupants of the building. Any comments on that?
Yeah, that's a good point, I think.
I couldn't catch your question because we have a storm, so it's very noisy behind me. I think that I mean, obviously, introduce nanomaterials into recycling concrete, it does have some kind of concern, the cost and also that is a safety concern. But all that amount of nanomaterial we introduce very small amount. It's talk about 1% or even less than 1%, and the format is mixing with the materials is in the solution format. So it's not dry powder. So we saw that it kind of risk to health and to of the environment will be very minimal. Okay? We do find that a very small amount of nanometer has an amazing effect, and to improve the properties such as ITZ. But most of the research we're doing with the materials is very expensive, and now we're trying to lower down that cost using we still call nanomaterials, but actually some are not nano. It's much bigger than a nano scale, but it's still called nanomaterial, like a nano clay. It's really not in a nano. It's more like 10 micro, something like that. But it's a good comments.
Yeah, I mean, regarding during construction, yeah, it's known that they will be in colloidal form and all those things. But this was actually raised in by one of the practitioners here. What happens if we need maintenance or anything? We need to pour the particular sample or anything. At that stage, they will be in dried form, and then they can possibly be airborne after that. So, would that require additional protection from the workers who are on site as well as the occupants of the buildings, or yeah, just that's.
I also mentioned, and also nano safety is obviously is very important and aspect when you deal with nanomaterials. But mostly, if you deal with powders, you are more sensible and to the environmental health of workers. And as I mentioned, our nanomaterial are mainly in the solution format, so it's not to reduce the risk. But sure, yes, that sounds special measure should be taken when you deal with nanomaterials. Yeah.
Thank you. Thank you.
Okay.
Thanks. I think one of the questions came from YouTube. Maybe perhaps Rohit or Surinder can answer. Do the present codes permit use of RCA for concrete grades above M25 for structural purposes?
Yes. So if you see IS 383, it has been revised recently in 2016. For plain concrete application, it doesn't restrict to any of the grade of the concrete. But yeah, if you're going with the pre-stressed concrete, they says it's not to be used. But for reinforced concrete, they say that you can use either fraction of the recycled concrete aggregate, whether coarse or finer, but not in the concrete structure having the strength more than 25 MPa. Okay, and for lean concrete, we can go with the 100% use. But with lean means less than M15 grade of the concrete. So yes, for more than M25, we can definitely go and we can replace up to 25% of both the fractions for plain concrete only. Yeah.
Let's see, there is, I think, one more question. Yeah, so how can we incorporate the use of recycled materials in contract agreements, BOQs, right? Made with contractor for using the extracted material again, right? So, because they will not be knowing about the properties of the material embedded in pavement structures 40 years ago, let's say, nor they will be having confidence or surety of achieving quality from the quality. So how do we get these materials, incorporated? So that what do you think? Anyone, either Surendra or Rohit?
If I can
take that.
Yeah, sure. Ram.
Yeah, so I think the question itself has the answer. Like we should start incorporating them in the contracts because while of course we need to worry about what exactly was the parent concrete and properties and influence and other stuff. So those are all actually the problems for the researchers that we have seen from our speakers. And of course, they have developed the technologies which are actually suiting how to produce good quality aggregates, and they are being utilized in recycling facilities. And what the practicing engineers should really worry about is just take the materials and use it appropriately, depending on the performance requirement that they face in their review. So it's just about taking quality assurance certificates from recycling facilities about the material properties. And of course, it all depends on how contracts are being structured. So once we have big specifications, of course, even standards are also allowing the usage of aggregates. And so therefore, people really should not worry about that. Practicing engineers should more be concerned about start using these in their regular applications.
Thanks, Ram. I think, Mr. Gaurav, you can unmute yourself and ask question.
Yeah, Piyush, 1 second. Dr. Kim is also here. She rejoined. She had a system failure, and then sorry for that, Dr. Kim. But yeah, we have already shared the video link with the participants. And if they have any queries, I request the participants, if you have any queries, you can directly connect with her.
Great, thank you. Yeah, sorry for the technical issue. I tried to rejoin, but somehow I couldn't. But I'm now using the last another machine. How about the last? I only left a couple of slides. Have you shared that with everybody? Or
so if you can share the PPT with us, so we can share with them.
We have got the PPT, sir. We have not shared it. Yeah.
Okay, we'll share with them then.
We'll share
because we have only last 2 minutes left for this workshop.
Yeah, sure. If you have good time, then I don't have to do it. Yeah, okay, good.
Yeah, but if they have any queries, I request them to get in touch with Dr. Kim. And then, like she mentioned, she's working on different projects related with the C&D waste. She is very active in LinkedIn also. And then she has the consortium. So, you can get in touch with her, whatsoever the social media is there. She's very active.
Only thing I can mention that there will be some workshops online and also in person in Southeast Asia this year and next year. So we'll advertise in our LinkedIn group. So keep an eye on that. Yeah, so we'll advertise that. Thank you.
Sure. Please share the link with us, Dr. Kim. Okay, so we have a good database we can share with all the people who are interested.
Yeah, sure, I will. Yeah.
Thank you. Yeah.
So, Mr. Gaurav, if you are listening, you can please unmute and ask question.
Okay. Hi, everyone. I'm a doctoral student here at the University of Manchester, UK, and even I'm also working on sustainable utilizations of waste in producing concrete. So basically, my question is with Mr. Rohit Prajapati. Actually, as you're working on the recycled goods aggregates, so I just want to know that when we are using the C&D waste in producing a sustainable concrete, does the study for the chemical composition of that recycled goods aggregates matter, or like have you studied that as well while conducting any test in a prior investigation? Because like suppose if you are using C&D waste which has been taken from a structure which was used for some nuclear shielding or it was exposed to fire, so I think it might affect the chemical composition of the recycled goods aggregate. So if we are using that in our construction part, so do you think it is going to affect the mechanical strength?
So the concrete which we are working on, we got it from a residential building. which was being demolished. So I'm not sure what can happen. But yeah, I think certainly we have to be careful. Like now there is a lot of discussion on leaching sort of maybe some metals and hazardous materials. So I think that should be a concern. But most of the C&D waste what we are getting are mostly from the commercial residential building. And of course, if some waste is coming from a nuclear plant or any chemical industry, I think we have to be careful with that. Yeah. But I have not worked on that. So in my case, it was coming from a simple building. So we did not have any problem with that. And in our process, we are basically removing the dead mortar. So we have not done any chemical test on coarse aggregates. No.
Okay, thank you.
Yeah, I think just I would like to add one point. It's a very important question, and I think that's going to play a big role if you really want to expand the use of these materials. So better understanding of physicochemical characteristics will be helpful if we really want to use the recycled concrete aggregate. So that's why we need more and more people working in this area so that we can make some difference. Now it's 6:01 p.m. here in India, so we have come to the end of this workshop. Thank you so much for your patience, and I hope it was really exciting to hear from speakers from different parts of the world about different types of research, not just material research, but policy research. And also you must have gotten some ideas for the future work where the potential is. Definitely, there is no doubt that there's tremendous potential in this area. So all of us, irrespective of where we are, can start working in this area and contribute. Thank you so much. I hope it was useful. And if you want any feedback, please feel free to give us feedback through the email which is mentioned in the flyer. And we are looking forward to your active participation in our future workshops, webinars. Thank you so much. Thanks to all speakers, all participants.
Yeah, thank you to everyone. Thank you to the organizing committee. Our students did a very good work this time. In fact, we didn't have to worry for anything. So thank you for the organizing committee also for taking care of everything. So if you have any doubts in the future related to the recycling or any other thing, please feel free to contact any of us. Okay, our email IDs are given in our website. So you have to just Google it, IIT Madras Department of Civil Engineering, and our the contact details will be provided. You can get in touch with any one of us anytime. So,
special thanks to UK team who made themselves available again. Take
Despite
care.
that
Hopefully next time we'll have an in-person workshop or webinars.
Thank you for chair and organize this workshop, and we hope we continue our collaboration, especially after the pandemic. We got a chance to see each other somewhere in the UK or in India.
Correct.
Okay.
Sure.
Thank you very much.
Thank you all.
Okay. Thank you,
Michael.
Michael.
Thank you, turn on the camera and we will have just a group photo.
Yeah, man.
Yes, good chatting.
So Sai Shri and Hariyappan, they were handling the whole workshop. Thanks so much.
No, thanks for your efforts, Rohi. Yeah.
So we'll just take a photo.
Gaurav, if you can turn on your camera, I think that would be great. Yes.
Okay, smile. Okay, thank you.
Thank you, everyone.
Thank you.
Hello, doctor.
Thank you, everyone. Thank you.
Thank you, Professor.
Bye-bye.
Thank you.
Bye.
Okay.
Thank you. Bye-bye.
Take care. Thank you. Bye-bye.
Okay.